Good morning, everyone. I see people are still flooding in from the login, so we'll give them a couple of seconds, but we're going to go ahead and start with our introductions. My name is Ebony Roan. I am your OPSERT program coordinator in the drinking water section, and today's webinar is focused on preventative and corrective actions for water systems. In some terms, this can also apply to wastewater as well. But as our program does focus on water treatment, so will our topics. I know a few people have been asking about wastewater training. Do not worry, they are coming up soon. Surface water and groundwater sections and ATQ are working on getting those out for you. Okay, a bit of housekeeping rules for our GoToWebinar guest. If you are in attendance today, you are earning professional development hours, and you can find the agenda in the handout drop-down section. It'll definitely say the title of this webinar, and you'll also find the PowerPoint presentations that you'll be viewing today as well in that handout section. Webcams are disabled and the attendees are muted, just so everyone can focus on the presentations. For any questions or comments, just go ahead and use the question drop-down box on the right-hand side. That should be right below your handout section as well. And if you don't see that drop-down option, if you have follow-up questions, please feel free to contact us at the azopsert@azdq.gov, or you can give us a call as well. This webinar is being recorded and will be available on our OPSERT training YouTube playlist within the next couple of weeks. Okay, for today's agenda, while there is an exhaustive list of things to cover, we're going to be focusing on 4 main processing systems: chemical feed pumps, O&M, and pump optimization, which will be presented by Joe Cornejo, a KEV consultant, operations consultant, and a certification trainer. We'll be moving on to, I didn't put the company, it's 2 PEs from Consor, Dane Whitmire and Leo Dell, as they'll be focusing on granule media, design and optimization. And then we'll wrap up the final hour with maintenance and inspection on still storage tanks by ADEQ's own drinking water inspector, Alex Valencia. All right, and since we've got a lot of information to cover, we're going to go ahead and move straight on to our first presentation. Joe, would you be able to take it away here?
Yes, thank you, Ebony.
Perfect. Making you presenter.
Okay, very good. Just confirming that you can see my screen, Ebony. All good?
Looks good. Carry on.
Okay, great. Well, good morning, everyone. I can see that there's several in attendance now, and the list just keeps growing for the seminar for this morning. I am Joseph Cornejo, and I'm very happy to be here this morning discussing this topic with you. Now, obviously, you could see the title on the screen. The topic of this first hour of the presentation is chemical feed pump O&M. The O&M acronym stands for operation and maintenance. And it's a very good question that we need to ask ourselves, whether we are operators who have been in the industry for many years, or maybe we're new operators who are just barely learning the field and becoming familiar with a lot of the aspects of treatment plant operations. The question is, why should we as operators be concerned about chemical injection pumps at our respective treatment plants? Well, one thing for sure is that water treatment plants inject chemicals into their process streams to remove contaminants, improve taste and appearance of the water, that is, make it very palatable, not only potable. And then very importantly, we inject chemicals into our systems to satisfy regulatory requirements. So it goes without saying that reliable and accurate delivery of these chemicals to the point of application is a critical function of our jobs as treatment plant operators. And that's why this presentation outline is going to be focusing on different types of applications of chemical feed pumps, different chemical types. We're just going to touch briefly on that. We're going to focus on the types of chemical feed pumps mainly used in the industry. And we're going to touch on some maintenance and some calibration. Now, mind you, this doesn't replace any type of manufacturer's O&M manuals for different pumps. This is just going to be limited to the basic operation and maintenance of these chemical feed pumps, after which it is recommended that you go to your manufacturer's manuals for the different makes and models of your different chemical feed pumps to get more detailed explanations of how they actually do operate. So it goes without saying that there's many chemical feed locations that exist in a treatment plant. For instance, many of you in your treatment plants probably have rapid dispersion of injected coagulants, and that happens in your flash mix or your rapid mix chambers. Some plants that they inject polymer filtrates, and these are added just prior to filtration or even on top of the filters. A lot of us, we disinfect our water as they leave our filters to preserve or to reduce undesirable byproducts. We use chemical injection pumps for this type of application. Chemicals are also injected to stabilize water, and once it goes into the distribution system, you inject corrosion control chemicals to stabilize the water. So the applications of chemical injection pumps are many. So just to repeat, the presentation will be touching on the different types of applications, the types of chemical feed pumps, and then some maintenance that is routinely done on chemical feed pumps, like priming of the pumps, like diaphragm pumps, and the tube change out of peristaltic pumps, and also the calibration of the pumps as far as how much volume of actual chemical they're injecting on a daily basis. Now, if you look at this next slide, it lists some of the more common liquid chemicals that are used in water treatment. So there's a lot of chemicals in addition to this list, but these are some of the basic chemicals that we see. Many of us are familiar with what is aluminum sulfate. It's one of the primary coagulants that we use chemical feed pumps to inject into our treatment systems. You see ferric chloride, which is another coagulant. You see the common sodium hypochlorite, which is your bleach that you use to disinfect your water. And we use chemical feed pumps for that. And then sodium hydroxide, which is caustic soda. Sometimes we raise the pH of the water by injecting this chemical using our feed pumps before it goes into the distribution system so that it stabilizes the water and then therefore doesn't corrode the piping in your distribution system. Okay, let's get into chemical feed pump types. When it comes to water treatment, chemical meter pumps are used to feed most liquid chemicals. Now, there are different types of pumps. You can see on my slide, I'm focusing on diaphragm and peristaltic. There are other types of chemical applicators like adductors, gravity feed systems, but a high percentage of systems nowadays use these two types of metering pumps. Now, diaphragm and peristaltic pumps are positive displacement pumps, and they're used for the purpose of chemical injection because they deliver a constant flow at a rated pressure. So whether you're treating water, and it could be you're treating wastewater, I know that there's some wastewater operators who are logged into the seminar. These two types of chemical metering or dosing pumps are often considered. Now, talking about these two pumps, let's focus first on what is diaphragm pumps. Now you can see in this slide, this is the front and back image of a diaphragm metering pump. So the question there is, what is a diaphragm pump? Well, a diaphragm metering pump is a positive displacement pump designed to operate as a proportional dosing pump. And what it does is it uses a flexible diaphragm in place of a piston to change the volume of the pump's chamber to increase and decrease pressure of the fluid inside. That is to say, these pumps deliver liquid impulses, and we're going to see this in a further slide of how they actually operate. But you can see here, these are the typical diaphragm metering pumps that are used in the industry, front and back. The next slide actually shows a picture of a diaphragm pump skid. Many of you have these types of skids at your water treatment plants, along with the necessary components of these skids. Now, if you look at the skid that we see here in the slides, it actually contains 3 metering pumps. A typical skid will have metering pumps for a particular chemical. In other words, typically you don't see a chlorine dosing pump right next to a caustic soda dosing pump right next to a polymer dosing pump. It doesn't work like that. Generally, a skid will cover just one chemical. And these 3 pumps are are basically installed to design to provide the specific chemical to a particular stage of the treatment process to inject that chemical, and they serve as backup pumps in case one or two pumps are not working. But one thing I want to highlight in this slide, and I don't know if you can see my mouse on the screen, but you have discharge and suction valves as part of the skid. You have the pump tubing, which is connected to the suction side and the discharge side of the pumps. And then you have pressure gauges up top, which, as already mentioned, these are positive displacement pumps. So the monitoring of the pressure that these pumps are putting out is very crucial to the operation of these pumps. You have pulsation dampeners here. As you can see in the movement of my mouse, these pulsation dampeners also control the output of pressure that these positive displacement pumps are putting out. And then you also see here, you see 3 calibration tubes, and we're going to touch on these calibration tubes a little later on in the presentation because they're very crucial to the operation of these pumps. And you use these calibration tubes to actually set the amount of liquid volume per day that these pumps are dosed out. So let's touch briefly on how these pumps work. So you see this is a cutout view of a diaphragm pump. So once again, I want to emphasize that a diaphragm, and another word for a diaphragm pump is a membrane pump. It is a positive displacement pump that uses a flexible diaphragm. This is a flexible diaphragm here. I'm showing you with a mouse on the curved portion of the cutout. And it moves forward and backward to form a temporary vacuum through the pressure difference. So right here, as it moves forward and backward, it forms a vacuum. And in forming a vacuum, it pulls liquid from a source tank, and then it discharges it out to whatever treatment stage of the process you want this respective chemical injected to. Now, these pumps are used to pump non-compressible fluids from one area to another. And diaphragm pumps have a pumping cycle that, once again, it consists of a suction phase and a discharge phase. And this diaphragm here, that is depicted in the cutout in red, serves as a partition wall between the liquid and the pump itself. Okay, passing on to the next slide. I hope the animation appears to the WebEx. But this animation gives a visual of how the suction and discharge action of a diaphragm pump actually work. So these pumps have a pumping cycle that consists, once again, of a suction and a discharge phase. As this piston pulls back, it pulls back the diaphragm, creating a suction. As it pushes forward, it creates pressure to discharge the chemical out into your treatment process. So this intermittent pumping of chemicals, specifically during the suction phase of the cycle, something that you need to keep in mind, sometimes can cause gas buildup in this pump head. And this buildup can be problematic because it causes vapor lock or loss of prime in these pumps. Now you notice here that in this animation, you see these little white balls here. These are actually check valves. And they have check valves at both the suction and the discharge ends of the pump head. Now, if either of these check valves becomes fouled, the pump or the metering or the diaphragm pump will not either will not pump or will not deliver chemical accurately. And another thing about these types of diaphragm pumps is that they sometimes cause shear stress on fluids, particularly if it employs a high velocity stroke action. So to try to avoid these problems, routine maintenance have to be performed on these type of pumps. And so they're very reliable pumps, but and they are a very cost-effective choice, but they do come with their particular challenges. And so that is why, because of these components, regular cleaning of the check valves and routine inspections of the diaphragms are necessary. Okay, so let's talk a little bit about the diaphragm pump and its advantages. One thing about diaphragm pumps, not only are they very inexpensive to purchase, they have excellent wear resistance. So that is to say that if taken care of properly, these pumps really do last a long time. So you do get a lot of bang for your buck when it comes to longevity of the pumps. And another thing is that these type of pumps have a very decent lifting capacity. In other words, that if your source liquid or your source chemical is below the suction level of the suction side of the pump, they have the ability to lift this pump up and also push it out a significant height. And it's very interesting to note that they say that these pumps actually have the ability to push chemical up to 6 meters. So that's referring to the vertical height at which the pump effectively lifts a chemical. And then once again, it has a good self-priming ability if you properly bleed out the gases. And we're going to touch upon that in a later slide on how to actually prime these pumps. That is to release some of the gas or vapor that may be locked on the suction or discharge sides of the pump, which can cause it to lose prime or prevent it from pumping. Another advantage is that this pump has easy maintenance, cleaning. It can work without oil for a short time. And it has multiple, is designed for most liquid types. And then so once again, the capacity of this pump to move material upward makes it an excellent choice for if you're pumping up elevations. A disadvantage of a diaphragm pump is that it has a very low operating speed, and they're not particularly energy efficient. And these pumps do not deliver fluid at a very high pressure. And then one thing also is that they don't handle off-gassing chemicals well, like for instance, chlorine gas. Chlorine gas, especially in the summer, tends to off-gas if you're using that 12.5% sodium hypochlorite. Sometimes the off-gassing of these chemicals inside of the pump tubing will cause what's called a vapor lock or a gas lock, airlock. And these pumps are susceptible to lose in prime because of that vapor lock. So that's one of the disadvantages that occur when using diaphragm pumps. So passing on to the next slide, let's talk about pump priming. Now you see two depictions of two skids here in these two illustrations, or these two pictures. Now one of them here, if you look where my mouse is pointing, is describing the system with suction lift. And what does that mean? You see the chemical source here. The chemical source is actually lower than the suction side of the pump. So that means that this system, the pump will actually need to be fully primed of air. And what I mean by fully primed is that you have to purge the air of the suction side tube before the pump could actually start sucking chemical out of the chemical source and discharging it to the process. So there is a method to priming these pumps, and that is using, most of these pumps are manufactured or built with an air bleed valve. And this air bleed valve is located normally in the top of the pump head. And then by turning that air bleed valve as a pump is pumping, it allows the pump to purge. Excuse me, let me go back to that slide. It allows the pump to purge the air out of the tubing. So then the suction side of the tube becomes primed with chemical. And then that way it allows the pump to lift the chemical up to the discharge line out to process. Now, the second image right here, you see it says system with flood exception. Now, this is a little bit more advantageous. In some treatment plants, you have your diaphragm pump skid right next to the chemical tanks. And sometimes these chemical tanks are relatively large, they're relatively tall, so that the chemical source level is actually above the suction side of the pump. Now, this is very advantageous because you have less of instance of getting of losing prime to the pump. Now, mind you, once again, talking about certain chemicals, like if we're talking about sodium hypochlorite, sometimes if the pump is left inoperable for a certain period of time, it could be several days or even several weeks, the chlorine will off gas and then fill the suction side tubing with gas. And then when the pump starts to run, this gas will form like a lock here, an airlock or a vapor lock, and then prevent the pump from actually pumping, even though the chemical source is putting hydraulic pressure on this on this suction side of the pump, putting hydraulic pressure, which should allow it to prime. But once again, if you off gas, then you need to open the air bleed valve to allow that gas to escape before the actual chemical will purge the line and then the pump will normally start pumping chemical to the discharge line out the process. So the manufacturers, the O&M manuals of the manufacturers of specific pumps, they'll detail how to operate these air bleed valves to properly purge the pumps of any gas or any air that may be on the suction side or discharge side of the pumps. Now, if you look in this next slide, it gives you a good depiction of what the actual backside of a pump looks like. The little red arrow here is pointing to the air bleed bypass line. So the way these air bleeds bypass line works is that they usually have a knob here. The knob could either be turned or it could be pulled depending on the model of pump that you're using. And when you do that, what it does is that it starts bypassing air through a bypass line. Now, right here in this arrow where my mouse is pointing, you see air bleed bypass line under the heading. So what happens is that when you pull this knob, it starts discharging the air, not into the discharge tubing because that could further add to your vapor lock, but out to a side piece of tubing or length of tubing, which could either be going to atmosphere or it could be heading back to the chemical source tank. But in essence, what it's doing, it's purging that air. It's getting that air out of your suction tubing, and it's not allowing it to go into your discharge tubing because air either in the suction side or the discharge side can cause that airlock, which will prevent your pump from operating. So once again, that is your air bleed bypass line that needs to be operated to help prime the pumps. So once again, when you are priming the pump, we're getting back to this skid that we saw earlier. Once you start the pump and you're making sure that all your discharge valving and your suction side valving is open, then you start your pump. In this case, if you're using a system with suction lift, you're going to start the air bleed line first. You're going to want to purge that air out of that suction side of the line and then fill it up with chemical. And then once you fill it up with chemical, then you're going to notice that it's going to be that you have chemical pumping out to your discharge line out the process. And one of the ways that you can tell is that you can visually see the chemical depending on the clarity of your discharge tubing. But let's just say that you have maybe colored tubing, some of the tubing that's connected to these type of pumps, it could either be black or sometimes it's yellow. So how do you know if you're pumping chemical? Well, another way to tell is that your discharge gauge here, your discharge pressure gauge, will actually start registering pressure. When there's nothing being discharged out of these gauges, they're going to normally read 0. But once you're actually pumping chemical, especially if you're pumping chemical up, these are going to start registering pressure, letting you know that you're actually pumping chemical. With a system with flooded section, sometimes you don't need to start the pump to actually prime the suction side line of the pump. You could actually open the air bleed valve, and the actual pressure, the static pressure from the level in the chemical source tank will push that trapped gas or trapped air on the suction side, and it will purge it out of the air bleed valve. So you can do it one or two ways. You can actually start the pump and then open up the air bleed valve like you would on the system with suction lift to purge the line a lot quicker, or you can just, without starting the pump, you can go ahead and open up the air bleed valve and then just let the static pressure of the source chemical tank push liquid through the suction side of the valve, purge the air out into the air bleed valve, out of the air bleed tubing, and once your system is primed, then you can start your pump, and then you'll notice that the pump will start discharging chemical into whatever stage of the process that this pump is connected to. Okay, so far we've touched a little bit on what a diaphragm pump is, more or less how they work, and how you actually prime a pump. Now let's get into the second type of pump that is used in water treatment, which is a peristaltic pump. Now this is another positive displacement pump. Now the image in this slide depicts a peristaltic pump with a pump mounted controller. That would be the image on the right side. and another pump without a mounted controller. Now, these type of pumps are typically preferred for low pressure applications and are able to feed chemicals over a wide flow range because the keeping chemical only contacts the tubing or the hose. And we'll get a more detailed explanation about this a little later in this presentation. So because peristaltic pumps are positive displacement pumps, they only move a fixed volume per revolution, and the movement of the liquid through these pumps is linearly proportional to the speed at which the pumps are turning. But one thing that is notable is that when properly calibrated, these pumps can achieve a metering dosing accuracy of plus or minus 0.5%. So that means that they're very, very accurate pumps for the application in which they're used. Okay, this slide shows a typical peristaltic pump skid. Now here you can see the picture of a skid. This one has actually two pumps connected or installed. And the same thing as we saw with the skid for the diaphragm pumps, it's got the same appurtenances or the same attachments to it. You got the discharge, and then you have the discharge and the suction valves. You have the pump tubing, the suction side tubing, the discharge tubing. You have your pressure gauges up top. You have your pulsation dampeners, and then you also have your calibration tube attached to these pumps. So how do these pumps work? Well, if you see in the image here, with a peristaltic pump, the fluid is pumped through a flexible tube. This is a flexible tube here. The blue color actually represents chemical passing through the tube. So there are roller assemblies here. In this case, this image has 4. And typically when these pumps, the way they're designed, they could have 2, 3, or up to 4 rollers. So far in the industry, I haven't seen a peristaltic pump with 5, but I wouldn't be surprised that there are some larger pumps that have more rollers installed. And as the rotor turns, these rollers pinch the tubing to force the liquid through. So these rollers, or shoes, they call these rollers also, in a peristaltic pump, they compress the tube or hose as they rotate. And what they do then is that they create a vacuum on the suction side, which draws fluid through the tube. So this gentle squeezing action of the tube and the valveless design of a peristaltic pump head results in the continuous injection of chemical into your treatment process. Now this animation in this slide, it gives a visual of how the suction and discharge action of a diaphragm pump work. So as you can notice, the pump rollers, they're spinning, and they're spinning on a pump shaft, which is not really depicted in the animation, but we'll see it in a further slide. So they're rolling, and as it rolls, it's pinching the tubing and trapping the chemical between the two rollers. And as the rollers compress or pinch the tubing, they're pushing the chemical forward, in effect also creating a vacuum on the suction side of the pump. And that's how they suck water from the source and they discharge it out to the injection stage of the process. So note that nothing but the pump tube or the hose touches the fluid. So this eliminates the risk of the pump contaminating the fluid or the fluid actually contaminating the pump. That's not to say that these tubes don't leak. They do leak, or that they can leak. And then if they do leak, it's obviously then that chemical is going to be discharged into the pump head. But during normal operation, chemical never touches the rollers or the actual pump head. So just talking a little bit of the advantages in operating a peristaltic pump. They're very easy to operate. Loading of the tubes or replacement of the tubes is very simple. Now we're going to go into a description of how to actually do that. And one thing that's interesting is, as opposed to diaphragm pumps, you don't need check valves. There's no check valve required because the actual pinching action of the rollers is what creates in essence, it creates a valve. So this requires no valve in its operation because one roller is always compressing the tube against the tract. And so when there's always one roller compressing the tube, this prevents backflow or back siphoning when the pump is not in operation. And then another positive about peristaltic metering pumps is that they're very good at pumping fluids that contain particulate matter. They're generally designed to pump into low pressure systems. And another thing is that they have no valves to clog. And the gentle force created during the peristaltic pumping action is very effective for pumping fluids such as sodium hypochlorite. And why are we mentioning sodium hypochlorite? Because remember that sodium hypochlorite or liquid chlorine, it actually off gases. And so these type of pumps generally do not lose prime, even though there's gas in the suction side or discharge side of the pump. So as opposed to diaphragm pumps, they do not fail as opposed to losing prime, because the gas can be simply pumped through the tubing through the peristaltic action of the tube. And another thing is too that these pumps, as they need no priming, they could also run dry without damage. It's not saying that you want to run them dry, but if for whatever reason there's no chemical running through the tubing, it won't necessarily damage the pump or the tubing. Now, talking a little bit about the disadvantages of peristaltic pumps. Well, because there's constant pinching of the tubings by the peristaltic action or movement of the rollers, there's quicker wear and tear of the tubing. So this requires routine changing at regular intervals throughout the pump's life. And another thing is that it does not have a significant lift compared to that of a diaphragm pump. That is to say that on the discharge side of these pumps, you can't expect to lift up chemical as high as you would with a diaphragm pump. It doesn't produce as much pressure as a diaphragm pump. And then in applications where a disposable tube set is required, sometimes the tubes have to be replaced very often. There are some applications that you have to replace the tubes on a daily basis. So that could also be a drawback of peristaltic pumps. And you also have to be very careful that the tube changeover is correctly done to avoid compromising the performance of the top. So now that we're in the subject of tube changeout, let's talk a little bit about tube changeout in a peristaltic pump. One thing that we want to make clear is that when you're dealing with pumps, skid components and process piping can be under pressure. So prior to working on any portion of a pump skid system, be it a diaphragm pump or a peristaltic pump, you always want to make sure that the system is depressurized, the power supply is turned off, and then chemicals are drained from the lines. And then you want to flush and neutralize the area that you're working on, especially if you're working on chemicals like caustic soda or sulfuric acid, and then wear the suitable protection gloves, safety glasses, goggles, and the like. Okay, let's talk briefly about tube changeout. This is going to be a really limited description of how to actually change out the tubes, but it's going to give you a really good idea of how easy it actually is to replace the tubing on these chemical pumps. So the tubes need to be changed out based on use. Sometimes they get to the point that they're actually pinched flat by the rollers and they will no longer pump chemical. Or it could well be that if you leave them in there too long, they do crack from wear. And if you form cracks, and you're going to have chemical leaking inside of your pump heads, and then it's obvious that they're going to be requiring change out. But how do you actually do that? Now, this is a typical design of a peristaltic pump. And I'm not saying that all of them are designed the same way. Once again, for your particular model of peristaltic pump that you use at your treatment plant, you're going to have to refer, obviously, to the O&M manual that the manufacturer provides for that specific pump. But typically, the pump heads, the pump covers, they have 4 or maybe more cover screws. So when you take these screws off, you're able to remove the covers. And then right on here, you see the roller is on a shaft and it has a collet here. And then you remove the collet screw to take the roller off, and that way that you can remove the roller assembly. So once again, this is what these are just typical peristaltic pump um, uh, tube change out looks like. Very, very simple. So then what you have to do next is that you see this tubing here, this worn tubing, you remove it from the pump head. And then you inspect this collet for wear. And notice that the collet can remain on the roller assembly when the roller is slowly removed from the pump shaft. This is the collet here. You can see that in this image, there's no more roller assembly. Normally the roller assembly just clicks off. Or if it doesn't click off, it's gonna have a little screw or a little bolt that you unscrew to remove the roller assembly. Then what you're gonna do is that you're gonna clean the inside of this pump housing with a rag or any appropriate cleaning solution to remove any tubing residue, because sometimes as a roller is pinching on this tubing, little pieces of tubing actually end up inside of here. Or if you did form cracks in the tubing, you're gonna get a little bit of chemical in here, so you're gonna have to clean that out. So once you do that, then you reinstall the roller with a collet onto the pump shaft. And you can see that there's a slot here in the collet that what's called a flat drive tang on the gearbox has to slide into. So you orient the rollers onto this slot tang to get the rollers back onto the gearbox shaft. This is something that came from the O&M manual of a particular peristaltic pumps that we operate at one of the facilities that I'm actually responsible for. And this O&M actually gives you some instructions on how to cut the length of the tubing. In this case, this is like a 3-inch diameter roller. So it recommends an 11-inch section of tubing. So what you have to do is that once you have the replacement tubing, you have to make sure that you measure out and cut an 11-inch section of the tubing. And mind you, you have to leave sufficient excess on the suction and discharge side of the pump for the desired connections. And you're going to see that in the next slide. So if you leave the excess intake tubing in a coil near the pump, it will make it easy to feed a new section of the tubing through the rollers when the section of the pump becomes worn. So what you want to do then is you want to install this tubing into the pump head. And one thing you have to be very careful of is sometimes when you're installing this tubing, sometimes it can develop a twist. So you have to really make sure that you examine the tubing for this condition and you untwist it. And it's very easy to do that. You just you turn one in the tubing where the twist exists, and that way you eliminate it. But make sure that it has no twists when the tubing is installed in the pump head, because if it does have a twist, I guarantee you're not going to be pumping chemical, and you're going to develop a crack really quick in the tubing if this is not taken out. So once the tubing is installed, the pump cover is back on, and the screws are tightened. Right here on this side of the pump, you're going to have what's called a tubing seal clamp. And this is what actually keeps these part, the suction and the discharge side of the tubing from walking. You want to make sure that this is properly clamped down and that the tubing is immobile, because if not, as a roller spin, it's going to pull the tubing through the roller. And in essence, your installation is not going to work. So you do not want tubing walk and tubing being pulled through the roller. So you want to make sure that these clamps are properly adjusted. And then once the tubing is installed, then you can put the appropriate adapters onto the tubing, and then you can make sure that that your pump is now in operation, that there's no leaks, there's no visible twists, and that is properly discharging into your treatment process. Okay, let's touch on chemical pump calibration. Now, this pump calibration is the same for both the peristaltic pump and the diaphragm pump. So these type of chemical metering systems, they're designed to provide chemicals at precise flow rates. So metering of the pump output can be set as a function of both stroke length and stroke frequency. And sometimes when it comes to the peristaltic pumps, the amount of spins that the rollers are doing on the actual pump shaft control the output. And then when it comes to diaphragm pumps, you have what's called the speed, which is a speed and a stroke. The speed of the pump is how many times the diaphragm is going to pulse, and the stroke is how deep the diaphragm is going to actually push and pull. So the deeper the stroke of the pump, the more chemical that it's pulling, the less deep, the less chemical that it's pulling, and the speed just basically dictates how fast a stroke frequency is being completed. So how do you go ahead and calibrate these pumps? Well, a calibration column, and you can see in this image, this is a calibration column. It is used to determine the flow rate and to enable adjustments to these pumps to make sure that it's properly calibrated and that you're injecting the type of flow or the chemical dose that you want for this respective chemical that you're using when performing the calibration. Okay, now this calibration is periodically necessary to ensure accurate chemical feed. Maybe you're asking yourself, well, how often do I need to calibrate these pumps? Well, the frequency of the calibration is going to vary, and it's going to depend on the stability of the pump. It's going to depend on the type of chemical that you're feeding, and then the different type of treatment conditions. So you will determine with experience through your specific treatment process how often you need to calibrate the pump. So just as a general rule, most chemical metering pumps need to be calibrated at least once a month. And it is very important that a calibration column be installed, because this will facilitate the periodic calibration of the pump. But I just want to make a side note here that if you do not have a calibration column, then there's other ways to calibrate these pumps. And one way would be to actually have like have some type of measurable volume on the discharge side of the pump that you can capture chemical as it's pumping, and then once you can determine the volume of that chemical during the time that it's pumping to see how more or less accurate your pump is pumping chemical onto your discharge process. So once again, many of the metering pumps I mentioned, they have the adjustment for both stroke and speed. And then when it comes to the peristaltic pumps, well, the amount of rotation of the actual rollers determines how much pump you're actually pumping. So what is the calibration procedure for metering pumps? Well, it involves these several steps. Now here you can see in my slide the different components. You see your calibration column, and then you have your suction and your discharge valves. So the way that you calibrate a pump, and I'm gonna focus on just on the description on the diaphragm pump calibration. You set the pump speed and the stroke at a setting desirable for whatever dosage that you want. You're going to set that stroke and that speed based on whatever dosage that you've been or that you've estimated or calculated to be able to pump into your system. And what you're going to be doing is that you're going to fill this calibration chamber or this calibration column to the top or to a point of measurement that you can begin your calculation with. And then once you do that, you're going to manipulate this valving so that you isolate this metering pump to the calibration chamber. That is to say that once you fill this chamber, you do not want chemical discharging out into the system, because then it's gonna give you an inaccurate calibration. And what you're going to do is that once you fill this chamber, then the pump is going to be pumping chemical from this chamber, and as this chemical is being pumped down, you're timing the pump down of the chemical in the chamber, and then based on how much graduations have dropped when you started your timer, then you can begin to then calculate how much you're pumping. So then once again, you want to fill this up. You're going to zero your timer, and then you're going to begin pumping from the calibration to chamber. So when the chemical starts to drop, that's when you begin your timer. And then you're going to the chemical for a measured time period. The longer, the more accurate. There's some operators that like to pump for 30 seconds. Some will do up to 3 minutes. Some will do even longer than that. So once again, the longer you can do it, and that's going to be contingent on the size of your calibration chamber, the more accurate your actual flow measure is going to be. So in this next slide, you can see how this is actually a representation of your calibration chamber. So the calibration chamber or column is filled to slightly above the top mark of the scale. So the pump is then run in the system being fed from the calibration column. So let's just say that we're just doing it for 30 seconds. So after a 30-second timer or time period, the liquid level reader on the scale will be a direct reading of the pump flow. And it could be in gallons per hour, or it could be in milligrams or in the milliliter scale per hour. But that measurement is going to actually give you a good indication of what your pump rate is. And based on this real pump rate, then you can see how accurate your pump is actually pumping. And then, like stated in a previous slide, it could be that your pump, especially like the peristaltic pumps, they're 0.5 plus or minus % accurate. And the diaphragm pumps are generally 5% plus or minus accurate. But the only way that you're going to really know what you're actually pumping is by doing this calibration procedure. Okay, so I want to thank you for your participation, your presence during this presentation. I hope this brief presentation on the basic operation maintenance of a chemical feed pump has served to your benefit. So once again, I just want to emphasize the real guide to the detailed operation and maintenance procedures for your plant's chemical feed systems will be found in the pump manufacturer's O&M manuals. So thank you very much for your participation. Now we have a few minutes left. If there's any questions from those in attendance for your presenter, I'd be more than happy to answer them.
Thank you very much, Joe. Great presentation. Someone brought up duckbill valves earlier. Do you mind explaining to the audience the importance of duckbill valves and the chlorine injector?
Duckbill valves, I don't really use those too much, but normally the duckbill valves, it's exactly what you see. It's like it has a function of like a check valve, because liquid can be discharged through the bill of the valve. So because it looks like a duck's bill, it's actually really, it's flat. It doesn't allow chemical to come back in. They're normally on the suction side of these. I've seen these on the suction side or on the discharge side of these chemical feed pumps. I just want to give you, based on my personal experience, I don't particularly like them, especially in certain applications of chemical, because they do get buildup on them. And then once they get buildup, they don't operate properly. But I said, I don't particularly favorably use a duckbill valves. They are low in cost, but they do get buildup, especially using chlorine or another chemical like ferrochlorine.
Awesome. Thank you very much for that. If you guys have any more questions in the audience, please add them to the drop-down questions box. Joe, if you want to go ahead and take time, you can go ahead and switch to the next presentation. And if any other questions come up, we have one more that just came in. Sorry, Joe.
Sure.
What adjustments would you make if the calibration is off? Calibration for your pumps.
Okay, yeah, for instance, there are some treatment plants that you're actually connected to like a SCADA system, where the SCADA system is actually controlling the output of the pumps. And you can make an adjustment, you can make a digital adjustment or correction for the output of the pumps in this case. But generally the way it works, if you're at a smaller treatment plant and you don't have this type of technology available, if your pump is off, let's just say that that at a certain speed or a certain stroke that you think that you're putting out a certain volume, but once you actually do the drawdown on the calibration chamber for that speed and that stroke, and that you realize that you're off, you have to basically you have to record the amount of volume that you're pumping. Let me see if I can say this in the simplest terms. Let's just say you have a pump, a diaphragm pump, and at a speed of 30 pulses per minute and a stroke of 50, which is 50% of the actual diaphragm pump length volume. This is say you were doing before, you were probably doing 4 gallons a minute. So after maybe several months use of the diaphragm pump, you go and you're trying to recalibrate it again, and you're still set at that same speed and you're still set at that same stroke. And after your timer, instead of doing 4 gallons a minute, now because maybe your diaphragm was a little bit more worn, or maybe some of the components of your pump are a little bit more worn, now it's only doing 3.5 gallons per minute. Well, that's where you need to record that. Okay, at a stroke of 50 and a speed of 30, I'm actually doing 3.5 gallons a minute. And then using that 3.5 gallons a minute, then you can use math calculations to determine what your actual daily dosage is for that pump. But that's the whole purpose, is that unless you have an electronic means, which some of the manufacturers nowadays, that they could actually, they have a digital way of saying, okay, at 30 speed and at a 50 stroke, I'm actually doing 3.5 gallons per minute, which is equivalent to, well, what have you, 30 milligrams per liter of chemical going in a day. Then you can digitally make that adjustment on the pump controller. But if you don't have a pump controller, then you have to do it the old way. You have to manually record and say, okay, at this setting, this is what I was getting, and then you write it down, and that's how you know where your pump is calibrated at.
Awesome. Thank you very much, Joe. But you also bring up a good point, record maintenance, good record keeping, so you know if something's going on with your pump in the long term. So we'll follow up with any other questions here. Can you touch on the importance of pulsation dampeners?
Well, remember we made mention, I think I repeated several times, that these are positive displacement pumps. So what that means is that you can't operate these pumps against a closed discharge valve. If you do, you're either going to destroy the pump, you're going to destroy the tubing, or you're going to destroy the valve. So what these pulsation dampeners are is that they actually allow for some of that pressure to be dampened. They're pretty much self-descriptive. And these pulsation dampeners, normally they have like a little air pocket, but they have a spring inside of them that they will take some of that pressure away from the discharge side of the tubing. Sometimes it could well be that, for instance, I made mention that a peristaltic pump can pump against some head. So a good way to remove some of that pressure on the discharge side of the pump tubing is using these pulsation dampeners. I've seen sometimes that there's some operators that after they stop working, they just take them offline. They just valve them off, because normally the pulsation dampener has a valve that will isolate it from the skid. And the pumps will work sometimes just fine, because why? Because you have your discharge valving is open and you're not pumping against a closed valve or a closed head. But what these dampeners actually do is that they preserve the life of that tubing, they preserve the life of that pumping, so that you don't have as much pressure on it. So you're less likely in the long term to develop leaks in the tubing or the piping. And that's why you want to have these pulsation dampeners. I hope that answered the question.
Sounds good. Thank you so much, Joe. All right, if there are any more questions, we're going to hold them after the next presentation, Joe, if you'd like to prepare for pump optimization. We'll go ahead and take a quick few-minute break. It's going to be very quick, 5-minute break, while Joe prepares for the next slides.
Thank you.
All right, this, this. Once again, copies of these presentations for Joe's presentations and the presentations you'll see later on in the hour. Bless you.
Excuse me.
Um, no, you're okay. Are available in the handout section. If you, excuse me, for some reason do not have the handout section or it's not visible on your end, I know on the phone or a tablet it can be a little bit difficult to find, please email the azopsert@azdeq.gov. We'll go ahead and make sure you get copies of those presentations, including the agenda. So for anyone who's just tuning in, we just covered chemical feed pumps, O&M. Next, we're going to be going into pump optimization, which will also be continued by Joe Cornejo as well. After Joe's presentation, we'll be taking a break around 10, 9:50 to 10 or 10 to 10:10, depending on the time. And then we'll go ahead and wrap up with the last two presentations for the day. If you are in attendance for the full webinar, you will get 4 PDHs earned just for attending. If you're only staying for a couple hours, of course, our records will show you only were here for a couple hours. Please mark your agendas as such. And for anyone who is in attendance and maybe watching with a group, I highly suggest registering and then making sure that the OPSA program knows that you were in attendance. We do have to verify your attendance for these webinars. If in the future you need to verify your own PDHs or you lose a copy of your agenda, we do want to make sure that you were in attendance, just to be fair to people who were here for the full 4 hours. Here, perfect. Then also from Brian, there was nice presentation. Kudos to your chemical feed pump, Joe. Also, while Joe is preparing for his presentation, I'm also going to go ahead and let everyone know, if you're not signed up to receive notifications for the OPSERT program, please do so on our homepage. Let me go ahead and let you know. We have quite a few events coming up in 2024, but I'm pausing my screen, please. But just so you know, if you're not signed up for notifications, please go down to workshops, receive notifications, and then you can sign up with your own email. Why is this important? Because this is how we will let everyone know that we were doing an outreach event. And then you can also go here as well to see any upcoming events for OPSERT. Currently, right now, we have Water Treatment Math 1 and 2 and Water Treatment Math 3 and 4 next Thursday and Friday in Flagstaff. The class is sold out at the moment, but we will be bringing these, we will be rotating the water treatment and water distribution math classes throughout 2024. Also, we do have a PFAS workshop coming up November 6th from 9 to 2. This is a hybrid event, so you can come in person, which will be registration through Eventbrite, or you can sign up to view virtually, which will be registration through GoToWebinar, the same platform you've all joined today. If you're not registered or you haven't heard about this event, you get the notifications, you can always go to the ADEQ OPSERT homepage, go under workshops, go back. Going to workshops, prepaid workshops, because all ADQ workshops trainings are prepaid. They're free for you for attendance. And then you'll go down to upcoming events. And right now, if you look under view details, they'll show you all the registration information, including the topics that we'll be covering from 9 to 2 that day. If you are in person, please keep in mind that this event will be held in at the ADQ Phoenix office on the 3rd floor. and of course, the go-to webinar for virtual attendees. Joe, let me know when you're ready.
I'm ready, Ebony, thanks.
Perfect. Go ahead and pass the screen to you.
Okay, can you see my?
Looks good.
All right, great. Okay, everyone, thank you very much for being present for the second hour of this seminar. The first hour we talked about pumps, notably chemical pumps. Now here you notice the title of this presentation is actually called Pump Optimization. And when you use the word pump, you say, hey, you're painting with a very broad stroke. What type of pump are we going to be optimizing? And then the word optimize itself also paints with a very broad stroke because there's so many things that you can do. And then you could probably say, well, as an operator, there's only so much. It's like I install the pumps, I didn't design them, so how can I actually optimize them? And don't worry, we're rushing going to get into some things that can be done on an engineering level, but also maybe some certain practices and some certain tools and some certain applications that treatment plant operators can implement at their treatment plants for their respective pumps. And we're going to be talking about actual water pumps to optimize their use, and then the pump life, and then the cost of running those pumps. So water actually is vital for our daily lives, especially here in the desert. We use water for drinking, washing, growing the food we eat. So whatever the nature of the job that we're using water for, we need to install water pumps. And what water pumps actually do is that they move the water, and it's not an easy thing for water pumps to do that, because you remember from your operator training, some of the math classes that you took, you know that water weighs approximately about 62.4 pounds for every cubic foot. So what that basically means is that moving water requires a lot of energy. And there are a lot of crucial components in moving drinking water. You have a distribution system. And there are certain factors in the distribution system, such as demand, available water supply, environmental sustainability, as well as the financial implications that need to be taken into consideration when operating water pumps. So that's what we're gonna try to touch on in this presentation, that there are opportunities for improving pumping system performance to actually increase the efficiency of these pumps, and hopefully reduce utility operating costs when it comes to operating water pumps at distribution systems and water treatment plants. So we're going to discuss ways in which you can make the water pumps in your premises run more efficiently. Now, there are potential savings that can be achieved from the efficient use of your pumps. So pump optimization is a crucial factor. For instance, you want to ensure that the types of pumps that you're using for the different applications are correct. That's why pump selection is very important. Also, you want to make sure that the piping and the valves in which your pumps are connected to are sized correctly, that the valves are in good working order, that there's no leaks in your piping. So ensuring that everything is well designed and working correctly, that aids optimization and minimizes costs in operating your pumps. Remember that systems, generally the highest operating cost in most systems is actually the pump costs. It's more than 50% of your actual electrical bills in running your distribution systems in your facilities. And then this article is also going to touch, this article is also going to touch on controllers that can be used, namely like VFDs, pressure controllers that can be used for the efficient operation of your pumps in your respective sites. And then also it's going to touch on a little bit of maintenance that can be done to pumps so that they operate more efficiently. What type of pumps are we namely going to be talking about? Now, in the water treatment industry, the main pump 95% of the time, the type of pump that you're going to be using is a centrifugal pump. So we're going to be focusing on centrifugal pumps. So the centrifugal pump is always a preferred hydraulic pump. Once again, the statistic is that it's used in over 95% of industrial and domestic application. And why do we like centrifugal pumps? Because generally they're low in cost, they're easier to maintain, they're simple to operate, and then for that reason, that's why they're so widely used in the industry. You see them whenever you visit water treatment plants. You see them whenever you visit certain distribution systems. All right, so let's get into the topic of pump selection. So you want to select the right pump for your application based on how much you're going to use the pump. There was a recent study that found out, it came out in one of these trade journals, that the pump efficiency is on average, this is a very interesting statistic, it's on average 40% less in pumps installed in the water industry, and they operate at least at a 10% efficiency or less. Okay, so let me repeat that. It's that 40% of the pumps installed in the water industry operate at a 10% efficiency or less. Now that's a very significant statistic. So that would mean that sometimes the pump that's being used in a certain application is either not the right type of pump, or it could be that the pump is not the right size. And if it's either too big, then it's not operated efficiently, because first of all, you're not going to be using the pump at the right pump curve. And if it's too big, you're using a lot of electricity, and the pump is turning off and on, and it's not efficient. And it could be also that if the pump is too small, the pump never turns off. And maybe the pump is also constantly running and using up a lot of electricity. So the size of the pump is very important to optimize the operation of the pump. So getting into the size of the pump, one of the major drawbacks during design of a pumping system is actually oversizing. So what that means, it means that the flow and the pressure are often 25% more than what's actually required for the system. Now, system engineers, they have to usually work along with the pump manufacturers, and sometimes with the input of operators, to help select the right pump, ensuring that all the factors like the size, the power, the speed, the drive of the pump, secondary equipment, are ideally matched to whatever is going to be needed for this particular system. That's why it's very important to choose the right pump size. And choosing the right size ensures that your pump is highly energy efficient. And once again, I'm going to repeat the statistic. This is crucial because centrifugal pumps generally, they account for about 50% of the actual electrical cost of a facility or pumping station. And if these are not properly sized, they can run too much or run inefficiently. Well, and that's going to result in high electrical costs, high maintenance and repair costs. What happens a lot, especially when systems are designed, is that engineers often make the mistake of adding too much safety factors. They make the pump oversized, and that leads to those higher energy bills and higher maintenance costs. That's why the correct sizing is vital. So a good thing to determine is the actual working conditions. And I've experienced this a lot when I was working in the field, is sometimes we'll buy a pump and we buy it too big. And why do we do that? Because they say, well, in the future, we're going to be making more water. We're going to be processing more water out to the distribution system. So instead of buying a pump and having to replace it later, let's just go ahead and buy a big one now, and then operating as the system grows, and we'll just, the pump will be correctly sized to the system as it is growing. But that is generally, when it comes to the optimization of the operation of the pump, it's generally not a good practice, because if a pump is oversized, it's going to operate out of its curve. It's going to draw too much electricity, and without even realizing it, you can actually do more damage to a pump if it's not properly designed to the system that it's pumping volume and pressure into, and it'll actually shorten the lifespan of the pump. So there's a lot of due diligence that needs to take place when you're sizing pumps for a system. Now let's talk a little bit of classification of pumps for the type of flow that they have. So we were talking about centrifugal pumps. Now, centrifugal pumps, there's different types of centrifugal pumps. And centrifugal pumps also have different types of impellers, and we're gonna touch on these two aspects. But just talking about the classifications by flow, centrifugal pumps are classified in 3 flow classifications. Now, if you look at my screen, these 3 flow classifications, you got radial centrifugal pumps, you got axial centrifugal pumps, and then you got mixed flow centrifugal pumps. So each one of these flow classifications has an application. And then as operators, especially our operators on smaller facilities or packet treatment plants, it's very important that we understand the classification of pump that we're applying to our treatment processes, because it's going to make a big determination of whether we're properly, efficiently optimizing the use of that pump or not. So let's get into what these actually mean. One of the classifications of pumps is a radial flow pump. This is the most common type of centrifugal pumps that you're going to see in treatment plants and distribution systems. So these radial flow pumps, they're called radial flow pumps because they discharge liquid perpendicular to the main pump shaft. You can notice that in this slide here. This represents, this pink image here represents a cross section of the impeller. And so what this does is that this type of pump, the fluid comes out of the impeller at 90 degrees of rotation relative to the suction. So once again, the most common centrifugal pumps that we see in water treatment plants and distribution system are in the radial flow pump category. So fluid enters the horizontal suction flange right here and exits through a vertical flow flange up here. So the discharge is perpendicular to the shaft of the pump. So this design is to apply when there is a flow limitation and you want to raise discharge pressure. So a lot of your distribution system pumps, they're normally going to be the radial flow pump type because they create pressure. And that's why these are favorable for that. Now in this next image, you could actually see an animation of how these radial flow pumps work. You see the actual perpendicular suction of the water entering the volute in which the impeller is rotating, and you can see that the discharge is actually 90 degrees to that perpendicular, 90 degrees horizontal to that perpendicular suction. So this design is applied when there is a flow limitation once again, and you want to create pressure. Okay, let's talk about mixed flow pumps. Mixed flow pumps discharge liquid at an angle exceeding 90 degrees relative to the pump shaft. So here's a cutout section of a mixed flow type pump. You see the impeller right here, and you see the discharge. Generally, the discharge is 90 degrees, is an angle greater than 90 degrees relative to the pump shaft, which is right here. So mixed flow pumps, these are not as common. They're lesser known variants of centrifugal pumps, and they have a mixed flow impeller. So the fluid flow within these pumps undergoes both axial and radial pump in action. So these are not generally a staple in treatment plants, but they are used in many industrial applications. And as the name implies, in a mixed flow pump, you're mixing the fluid flow between radial and axial properties. We're going to get a little bit into axial pumps in the next slide. So these mixed flow pumps actually do both things. Generally, these type of pumps, they have a high flow rate. They don't build as much pressure, but they can pump both clear liquids as well as very turbid liquids or liquid with solids. The interesting thing is that you see most of these type of pumps, you see them more in wastewater plants because these type of pumps, they can handle water that has solids in it. I've seen applications sometimes in wastewater plants where you see these type of pumps, or sometimes you see in a wastewater plant where you have like a wastewater plant lift station that has a lot of solids. And instead of using a mixed flow pump, what are they using? They're using the pump that we saw on the previous slide, which is an axial flow pump. And it's not the application. What happens is normally that these pumps get plugged up a lot or they get worn down really quick because that's not the design, the proper design for these type of pumps. Okay, let's talk a little bit about axial flow pumps. So you see these are generally called propeller pumps. And axial flow pumps are used for low pressure, high flow application. There's almost no radial force imparted onto the liquid, so you can see it's not flowing in a 90-degree angle perpendicular to the pump shaft. Yeah, most of this, the movement in this pump is radial. The significant application of this pump is when there's a large flow rate and very little pressure head. So they're mainly for moving volume and for recirculating water in a tank. So they're not the type of pumps that you're going to see like in a distribution system because why? Because they don't build pressure. Okay, let's talk about impeller types. Now it's very important that we know that the type of impeller that we're using for the type of application in our pump is a correct one. Now there's three types of impellers used in centrifugal pumps. You have the open impeller, you have the semi-open impeller, and then you have a closed impeller. And each one of these impellers has their application. Like I used the example previously, if you're not using the right impeller for the right application, you're not optimizing the use of your pump. For instance, the open impeller has its application. Now let's get into that. Let's get into that, the open impeller. So this is an image of an impeller. As you can see, it doesn't have a shroud. In other words, there's no metal covering the vanes. There's no metal on top of the vane or behind the vane. So open impellers have the vanes free on both sides. Now, what is this type of impeller used for? Well, this type of impeller is ideally suited for pumping high viscosity liquids and liquids with many suspended bodies. So once again, these are really good for wastewater treatment plants or for like any type of sewage plant where you're dealing with a lot of pulp, paper pulp, a lot of solids. And sometimes the center of an open impeller is fitted with like a little knife, like a serrated knife, and to chop suspended bodies as they are drawn into the eye of the impeller. So these are designed to chop things and to handle a lot of solids, but they're not ideal for producing a lot of pressure. So this type of open impeller, if you have a clean water application at your wastewater treatment plant, it's probably not the ideal design. If you do know that you have at your plant a pump that has an open impeller, well, you're probably going to have to review the application of that type of pump in your process and to see that if it's the most efficient impeller for the centrifugal pump that you're using. Let's go ahead and talk about the semi-open impeller. As you can see, this one's a little bit different. Why is it called semi-open? Because this time the vanes, and these are the vanes of the impeller. This is actually a plastic impeller, and this is a steel impeller. And you can see that behind the vanes, it's got a shroud. So the vanes are free on one side, and they're enclosed on the other in a semi-open. Well, there's another, they call them semi-closed impellers. So this type of impeller is used for pumping liquids with a moderate amount of suspended bodies. Semi-open impellers are not as efficient as fully enclosed impellers because they don't produce as much pressure, and the liquid is not guided directly along these vanes. So you're probably trying to think, where in a water treatment plant are we going to be using this type of impellers? And all these type of impellers are where you do have solids in the incoming water body. So they could probably be on the intake part of your treatment process. Maybe you have raw water ponds, and those water ponds contain water that's not been treated, and it may have some turbidity or may have some solids in there. So maybe the pumps that are installed that are moving that water into your actual treatment process are going to be the semi-open impeller type because they can handle a little bit of solids, and they do build some pressure. Okay, let's talk about the third type of impeller. This is the closed impeller. Now, if you notice, this looks very different because now you cannot see the vanes. So closed impeller are the type of impeller that have two shrouds. They have a shroud on the front of the impeller, and they have a shroud on the back of the impeller so that the vanes of the impeller are actually completely sandwiched between the two shrouds. Now, this type of impeller is very efficient for pumping low viscosity fluids with few suspended particles in that water. It has the greatest mechanical strength of all the impeller designs, and this is a type of impeller that you mostly see in your water treatment plants and your distribution systems, because they're designed mainly to pump clean water, but they can move volume, but at the same time, as they're moving that volume, they can build pressure. You know, some of our distribution system pumps are specifically designed to maintain pressure in the distribution system, because as they run, they're producing above 50 psi of pressure, because distribution systems generally have to run at around at approximately maybe 30 to 60 psi of pressure. So this type of impeller in your centrifugal pump would be ideal for that. Now, one thing that that also has to be taken into consideration, this probably is not something that that operators generally do in their shops, but sometimes some of these pump repair companies that we use for repairing some of our pumps, they could actually cut down the impeller to the correct size. Sometimes the impellers in some of our pumps, maybe they're a little bit too big, and when they're too big, they can produce too much pressure. And by reducing too much pressure, then the pump is not operating as efficiently because it's using up more electricity. So there are some instances in which the impellers are actually cut to the correct size, or actually shaved down. And like I said, some of these shops that do the repairs on some of our pumps some of these shops that we send our pumps to for repair, they have the ability to trim the impellers to make sure that the impellers are pumping according to the pump curve. And what this actually does is it actually also eliminates throttling losses of the control valves, because these impellers are not producing as much pressure, so it allows your system control valves to operate a little bit more efficiently. Okay, pumps are attached to pipes. So another key consideration in optimizing the function or the operation of your pumps is make sure that you have the correct size pipes. Now, if you notice in this image, we have some very large pipes. This is like 24-inch concrete pipe. And then on the other side, you have maybe with a 6-inch polyethylene or PVC type pipe. So an excellent way to prevent pressure from dropping in the system and causing a pump to run out of its curve is to make sure that you have the right size of pipe. Hydraulic friction causes a loss of a reduction of pressure when water moves from one end of the pipe to the other. So sometimes if the pipe is too small, you're creating a lot of friction, and this friction makes your pumps work harder. And so the right pump size connected to your pumps is also critical. And I mentioned, you're probably thinking as an operator, well, once again, I don't design them, I don't install the pump size. But it's a consideration that you need to keep in mind, that if the size of your pipes, if it's not big enough, then that's going to limit the efficiency of your pumps. And then once again, friction loss in the pipe is also a consideration. Here we have concrete pipe, which is rougher on the inside, as opposed to like PVC pipe, which is smoother. So that's going to also be a factor in how efficient your pumps run. So it's a consideration that needs to be taken into account when operating your pumps. So once again, I just want to repeat that factors that affect friction loss in piping, which include the diameter, the size, the roughness of the interior of the pipe, the length of the pipe, the flow rate that's being actually pumped with those pipes. And sometimes you think that bigger pipes are an advantage, but sometimes they're not, because if there's some pipes are sized too big, then you can't pressurize the pipe sufficiently. And then once again, your pumps are working too hard and they're operating outside of your curve. And this is just for reference here. How do you actually measure the friction loss in pipes? Well, there's different formulas that engineers use to determine that friction loss. There are calculations which aid with this. Right here in this slide, I'm depicting the Darcy-Weisbach equation. And it's an equation that relates the head loss, pressure loss due to friction along a given length of pipe. And it relates this to the average velocity of the liquid flow through the pipe. There's also other calculations that we may have heard about, and the ones like called the Hazen-Williams formula. Now, the Hazen-Williams is very similar to the Darcy-Weisbach. The only difference is it relates the flow of the water in a pipe with the actual physical properties of the pipe and the pressure drop caused by the friction. So engineers will use these formulas to make sure that our pumps are connected to the right type of pipe, and that type of pipe allows our pumps to operate within a pump curve. But let's get into a topic that we as operators have control of, and that has to do with leaks. So to make sure that our pumps are operating correctly, we want to make sure that we avoid leakage to optimize the pumps in our system. Because water leaks, not only do they cause structural weaknesses in pipes and are a sign that the piping system could soon fail, what they actually do is that they reduce the reliability of the water supply network. And they contribute to pumps running inefficiently. Because if you have leaks, that means that your pumps are working harder to maintain the pressure in your pipes. And they're also working harder to replenish the volume that's being lost through those leaks. So that's something that also needs to be taken into account. If we're distribution system operators or treatment plant operators, we want to make sure that we're constantly checking our distribution system for leaks. Because those leaks, as previously mentioned, they affect the operation of our pumps. Moving along, let's talk a little bit about valves. You also have to implement the right type of control valves in your systems. Now, the valves connected to our pumps, they're used to both control flow and pressure. And sometimes these are used, these reduce loss of energy. So as you use valves to throttle the flow, and there's some treatment plants that will do this. So sometimes they'll use the valve here in this image. This is a globe type valve, or they'll use what's called a butterfly valve. And what they actually do is that these valves will open or shut to control the flow. That's a cost-effective way of doing that, but it's not the most efficient way of doing that, because what you're actually doing is that you're choking the output of a pump. So instead of regulating the flow through like a variable speed drive, slowing down the motor, the motor still runs at 100%, but you're using a valve to throttle the flow, to actually shut the pipe down so that less flow goes to the pipe. And what are you doing is that you're actually deadheading your pumps. And what's in the long term, what that actually does is that it reduces the lifespan of your pumps, because they're pushing against against a certain head that creates more wear and tear on the impeller. It creates more wear and tear on the pump and the motor. So you want to make sure that you implement the right type of control valves so that they open and then they close efficiently, so they're not, in essence, creating a significant head on your pumps as they're operating. But if we do have a facility that has a capital to employ it, we want to use variable speed drives in the operation of our pumps. Another term for variable speed drive, the acronym is called the VFD. Now, these are highly effective in improving the energy efficiency and the optimization of our pumps. What do variable speed drives do? Well, they allow more flexibility in the operation they regulate the speed of the pump. Now, I made mention in the previous slide that there's some application in some treatment plants where you don't have a variable speed drive. So how do you control the flow output of the pump? Well, the pump is operating at 100%. The motor is driving that pump at 100%. So if we have valves that are controlled either manually or through some type of control system, those valves are opening and shutting, and they're actually throttling down the force of those pumps running at 100%. Now, the advantage of a variable speed drive is that it actually slows down the motor, so that if we want to have a certain flow, instead of choking down the valve and putting pressure against the pump, it's actually slowing the motor, making the pump slower, and that way producing the desirable flow. Now, I want to get into kind of a detailed explanation of what a VFD pump actually does. So the VFD, it adjusts the rotational speed of the pump to achieve the required or the desired flow and head. Now, you can probably add a VFD to any existing pump system to reduce its speed to meet whatever requirements you have out in your distribution system. So this is very advantageous because once you install a VFD, it itself varies the speed to suit the needs of your distribution system or your treatment plant. Now, this is very good if you have plans to expand the system in the future. Now, I mentioned that sometimes to save money long term, what we do is that we buy a pump that's a lot bigger than its application, and we run that pump at 100% against a valve or a certain type of pipe. Well, sometimes a VFD will allow you to buy a bigger pump, and you can run that VFD because it's going to slow down the motor speed and the speed of the pump output to meet your current demand. And as the demand goes up in your system, then the VFD could simply be ramped up to make the pump run faster, and that way it's a good way to not only save energy in the short term, but it also lowers capital cost in the long term. So up to 40% of potential savings in a pumping system could be reached with the installation of a variable frequency drive. It's interesting, there's some statistics that are of note when it comes to VFDs that they offer when they're installed. Obviously, there's a capital cost that goes into installing them, but long term, the reduction of the energy cost could be between 55 and 70% of the electrical cost. And notice this, the reduction of the maintenance costs could be between 20 and 35% long term. So this is one of the most effective ways that you can optimize the use of your pumps and your systems by installing these VFDs. And I also wanted to add that a well-controlled operation of a pump using the VFD, what this actually does is reduces the water pressure when the demand is low, and it also prevents hydraulic stress on your distribution system piping. Maybe you have an aging piping infrastructure and you can't maintain a certain pressure for a long time in the distribution system because you end up having a lot of pipe breaks. Well, a good way to eliminate that stress on that piping system is by the implementation, the installation of a variable speed drive. And then these variable speed drives have a very soft start to them. So that also eliminates like what's called water hammer out in your system, because your pumps don't just go full bore when they start up. They start off very slow and they build up pressure very slowly in the distribution system. So they also protect your distribution system piping. So the implementation of variable speed drives is a very good way that you can actually optimize the use of your centrifugal pumps. Now, maybe you work at a smaller treatment system where maybe there isn't the capital or there isn't the budget to go ahead and install a VFD pump. Well, another more low-cost method to control the operation of your pump is by using pressure switches. This method is very often overlooked because it's one of the easiest ways to save energy and cut down on unnecessary use. The way that these switches work is that they're very efficient. As you can see that they have these pressure springs on there. And these springs are connected to some electrical switches that have about a 40 PSI to a 60 PSI pressure setting. So when, let's just say that this pressure switch is connected to the discharge side of your centrifugal pump, when the pressure drops to about 40 PSI, or it can even drop up to 30 PSI, I've seen that the range go down even further on these switches. I've even used them at a cutout range of about 20 PSI. Let's just say that we adjust it to about 40 PSI. When it hits 40 PSI, it's going to restart the pump. And the pump is going to run, it's going to pressurize the distribution system or whatever piping that is inside of your treatment process. It's going to pressurize it till it reaches a setting that this other spring, this larger spring, is set to. And it could be 50 PSI, it could be 60 PSI. Once it hits that setting, once again, the pump is going to turn off. And that's good because then once again, you're not running your pump 100% of the time. This pressure switch is turning the pump off when you need to pressurize the system, and turning it off when the necessary pressure has been reached. And what are you doing when you actually do that? You're saving on electrical costs, and you're also saving on the amount of wear and tear on your pump and motor because they're not running as often. So this is another more low cost way that you can optimize the operation of your pumps and your system if it is that you do not have the capital or the budget to install a variable frequency drive. Okay. Another thing that can be done is that you can actually have a multiple pump skid, and sometimes these skids could even have different size pumps. Now, if you look at these two images here, you see a skid that has multiple pumps, but most of these pumps seem to be of the same size. Now, this is called a parallel operating system, and this multiple pump system is very effective when each pump runs individually and not always together. So sometimes consideration is given between a single pump versus a multiple pump or a booster pump system like that. So instead of just one pump operating all the time, you have several pumps that can operate. And depending on the demand and the pressure in the system, one pump can be operating because it meets the desired pressure and the desired demand at that particular time of day. But as soon as the demand goes up, then another pump turns on. And if you're still not meeting demand and pressure, then a third pump goes on, and so forth. And what this actually does is that this prevents one particular pump from running all the time. And normally the way these pumps are installed is that they'll cycle within each other. For instance, one pump will become the lead pump, and then another one becomes a lag, and it rotates in that lead lag configuration so that you get equal use and equal wear and tear on all the pumps. Now, in larger distribution system, you sometimes have two types of pumps. You have a main and a robust pump that delivers a large volume of water to the distribution system, but you also have like a small low flow, high pressure pump that keeps the distribution system pressurized during periods of non-demand. And that's what's called a jockey pump. So this is like a vertical turbine jockey pump. And these are really neat because sometimes, especially at night, you don't need as much volume. You don't need as much pressure to keep the distribution system pressurized. You just need a small amount of volume to keep that system pressurized. And so you're going to use a smaller pump. And so these jockey pumps are installed to run when the bigger main pumps are needed. And what are you doing? Well, you're saving wear and tear on the bigger pumps, which are also more expensive to work on and more expensive to replace. And you're cutting down on electrical cost. And these jockey pumps are normally designed, they're normally sized, notice this, for 1% of flow and demand, and a 10 to 25 PSI higher pressure range than the main distribution pump. So these little pumps, which are less expensive to repair, less expensive to replace, they'll save the lifespan and the wear and tear on the larger, more expensive pumps. So that's why sometimes a multiple pump configuration is another way to optimize the operation of your distribution and water plant, treatment plant, centrifugal pumps. Okay, we still have a little bit of time, so we're going to talk about maintenance. You can't talk about optimization of a pump or a motor without talking about maintenance. And there's two types of maintenance that need to be implemented whenever you're operating any type of mechanical equipment in your facilities. It could be preventative maintenance or it could be predictive maintenance. Now, regular maintenance checks are very essential because that's the way that you find out about deteriorations and loss in capacity and efficiency in your pumps long before this becomes a major problem in your system. So preventative maintenance is very effective. Now this includes, checking the routine system, making periodic adjustments, lubrications, removing maybe contaminants or debris that may be stuck in your pumps. But then you also have what's called, excuse me that, sometimes my slides jump. You have predictive maintenance. And predictive maintenance includes tests and assessments that aim to reveal potential deteriorating conditions. So What is predictive maintenance? Well, predictive maintenance is a strategy that relies on equipment condition data that of when maintenance is needed or can be considered a form of preventive maintenance, since it involves an anticipation of preventing future equipment failures. So, preventative maintenance is very efficient because it's maintenance when it's scheduled. But predictive maintenance is a different type of strategy because it tries to predict in advance when a pump is about to failure, and it uses certain metrics to do so. It monitors your machine metrics to use the data to monitor equipment conditions in real time, and then so it will notify your maintenance teams, the operations teams of potential equipment failures. And so this predictive maintenance should also be implemented along with preventative maintenance in optimizing the operation and longevity of your facilities pumps. Okay, so part of that predictive and preventative maintenance is a routine inspection of your systems. Sometimes that data will let you know that, hey, you know what, my pumps, they seem to be operating, they sound good, but they're not putting out as much pressure, they're not putting as much volume as they used to. And so periodic maintenance checks are very essential because you'll take the pump apart and you find out that you've got wear and tear, or you've got deterioration of the impeller or the actual pump volute and casing. And so periodic checking of your system, and this is done through preventative and predictive maintenance, will also allow for optimal operation of your distribution system pumps. And then pump seals and rings are very essential. Here we have an image depicting wear rings on a centrifugal pumps. So leaks from pipes are not the only problems that affect the optimal operation of a centrifugal pump. Leaks of the seals sealing your systems, they not only cause wet conditions in your premises because water is leaking out, but they also cause losses due to increased mechanical friction. So leaks that occur between the discharges and pump suctions reduce the volumetric efficiency of your pumps, and that's why pumps are installed with a wear ring. If you could see the movement of my mouse, you see what a wear ring actually looks like. And the purpose of a wear ring in a centrifugal pump is it allows the pump casing to run with a small clearance between the impeller and the pump casing, and this minimizes the internal leakage of fluid to avoid the actual damage of the impeller of the pump casing. Sometimes operators will remove these wear rings, but the purpose of these wear rings is to actually protect it and to increase the length of the actual pump, the actual internal components of the pump, like the impellers. So if no wear rings were installed, then the process liquid would be able to flow from the discharge to the suction side of the pump in pretty large quantities, and this could lead in up to a 4 to an 8% loss of pump efficiency. So once again, I stated that sometimes we as operators remove the wear rings from the centrifugal pumps, but it's not recommended. Even though you can operate them without wear rings, the resultant damage to the impeller and casing, well, it's going to cause a larger replacement cost and maintenance cost in the long term. What we see here also is a mechanical seal, and this is also an image of pump flacking, like flacking in a centrifugal pump. Now, mechanical seals normally do not suffer the same problems associated with pump packing. They're more effective than this type of seal in a system. Packing is normally cheaper of the two options, but it has a lot of disadvantages because as this packing begins to leak, then you tighten the lint, or you tighten the packing gland to minimize those leaks. And what that actually does is that it presses physically against the shaft. And what it slowly does, it creates a groove on the shaft, which later also needs to be repaired. So this type of packing is not as efficient as a mechanical seal because this puts undue restriction against the motor and the shaft and does not allow your pumps to operate as efficiently. So another more effective seal to use in a pumping system is a mechanical seal. Now, I have seen personally that there are some shops, some repair shops that have the ability to retrofit a pump that uses this type of graphite packing into a mechanical seal. And there is sometimes a very significant cost involved to do this initially, but long term, what it does is it actually contributes to the longer lifespan of the motor, the shaft, and the pump itself. So mechanical seals are another way to, if you install these in your pump, they're another way to go ahead and optimize the use of your centrifugal pumps. Well, I want to give everybody thanks for being present for this presentation. I hope that this brief presentation, although it was limited because we have only a certain amount of time on the basic optimization of pumps, has also served to your benefit. And then once again, I just want to realize that the real guide to the detailed operation and maintenance and efficient operation of your plant is the pump manufacturer's O&M manuals, which will detail specific maintenance intervals for preventative as well as predictive maintenance. And they will also depict the pump curves of where your centrifugal pumps need to be operated at. Okay, thank you everyone, and I look forward to any questions you may have.
Thank you, Joe. Great presentation once again. We did have a question earlier from Neil. Does a VFD pump system improve efficiency even if the pump is oversized?
I like your question. Now, it just depends on how much the pump is oversized. I mean, if you buy a massive pump, it's not going to make too much of a difference. But if the pump is slightly oversized to your system, it does make a difference. And like I stated in a previous slide, a VFD pump will allow you to buy a bigger pump because it's gonna operate that bigger pump more efficiently because the pump is not operating at 100% until your system grows. Let's say your distribution system grows to the size needed for that pump to run at a higher percentage. So in effect, yes, a VFD will effectively optimize the efficiency of a larger pump attached to a distribution system.
Awesome, thank you very much. If anyone has any further questions, please, you can direct them to the questions drop down, or you can even put them in the chat if that is an option for you. For now, though, if there are no more questions, please make sure you get a screenshot of Joe's email. We'll also have it at the end of the presentation in case you want to follow up with him for any questions or comments. Once again, thank you very much, Joe, for your time today.
Thank you. Thank you, everyone.
Okay, so we're just about time for a break. I'm going to go show my screen here. We're going to go ahead and take a 10-minute break. We're going to resume, well, it's going to be about 11 minutes now. We're going to go ahead and resume at 10 a.m. With our next presenter on granular media filtration. All right, we'll see you all in 10 minutes. All right, everyone, welcome back. We said about 10-ish minutes. I think this came out to be about a 15-minute break. So I hope everyone had a chance to go do whatever bio breaks, coffee, water, stretch. All right, it looks like we're going to unfreeze the screen. Let's see. Okay. Oh, I'm not even frozen. There we go. All right, our next presenter is joining at the moment.
I'm here.
Oh, perfect. All right, so we're going to go ahead and pass it on to Dane Whitmire for the granular media filtration design and optimization. Dane, I'm going to go ahead and pass the screen to you.
Okay. Can everyone see my screen?
Seeing your desktop at the moment.
Okay. That's the main item here.
All right, perfect. See your full presentation titles.
Okay, here we go. Lee, are you on?
I don't see Lee in the staff nor in the attendees yet, but I'll
Okay.
give him a call.
I'll get moving on through this, and as Lee comes in, he can join us. My name's Dane Whitmer. I'm with Consor Engineer along with Lee Odell. Lee is our technical water specialist here with the company, our regional lead. And then I myself am here in Arizona doing water wastewater design and a number of other things here with Consor. Just hop on along here and we'll talk about general gravity filtration and an introduction to it. And the goal here is to introduce the basics so that it helps you with the performance and maintaining your gravity filters. Hopefully some information is new, although as I was preparing for this meeting, I had a question. I was like, well, how long has filtration been around? And actually, it's not a new thing. There's been India texts from India that date well back into 2000 BC and 700 BC with hieroglyphics that depict filtration and the benefits of using sunlight and other forms of filters. And so I think the first patented filter occurred back in the late 1700s. And so it's just been improved, and we've been kind of keeping some of the things around as they go. And so the question is, how do filters work though? And for our typical traditional filters, I was of the mindset that it was a sieving process, or a straining process, but that's really not um, the way that it works, because you can imagine the filter media here, it's 0.8 millimeters in size, whereas a particle that is trying to capture is 5 microns. And for comparison, a bacteria is 2 microns and 1 to 2 microns. And so perspective, if you blow these particles up, imagine stacking a bunch of school buses and cars together and then throwing a rock or marble through it, and allowing that marble to try and pass through. So there's a lot of holes, and it's a lot of effort. So so what's happening down here? You can kind of see here's a scanning electron microscope picture of a sand particle, and it's actually catching or the deposits of the silica particles that are on top of it. And so that's kind of what's happening, is that there are transport interactions occurring at the surface and attaching to it, or whether it's getting caught on the particle itself, and so on. And so we can see a lot of times that as the filter goes on, or we call it ripening, that it actually improves capture rate, and that's because we're changing the surface condition of the media to be more neutral and acting as an attraction to the other particles. So the basic transport theory, or the idea of how a particle actually gets onto the filter media, is there's 3 kind of main ideas. One, This A idea is that it can get intercepted. It actually has like an adhesion to it. There's sedimentation where it actually falls on top of it. And then C, there's this diffusive property. If you recall, a high to low concentration idea, things in high concentrations flow to a low concentration. And so through the Brownian motion is what is called as the particle wiggles itself down through, that it eventually finds its way onto the particle. So these are how it typically occurs. And so everything is done to try and promote these types of adhesions or interceptions to the filter media. Now we've done a lot of studies, and we've found that you know, of course, like I said, a lot of studies over hundreds of years, right, of observations and things, that the we can improve our filtration removal with the given diameter of the media, right? So as if you can see here on the left, the smaller media has a better chance of capturing removal, but at the same time, its interaction is that the smaller media creates a higher head loss through it, and head loss translates into used energy. So the more head loss, the more energy we have to use to try and either pump the water levels up, or it takes the energy away and we have to pump it after we've done filtration. So media diameter is one of the things that we look at in filter performance. We can also look at the filter depth, that as the depth of the filter goes, that we end up removing more particles, but again, we increase our head loss. It's not as effective as it's showing here, right? That we're starting to taper off. The more depth we go, that the less the rate at which we're removing particles goes lower. And so then we also have the loading rate, or in other words, how much water are we actually putting onto the filters, you know, and we measure that through gallons per minute per square foot. So a math question here, if we were taking gallons per minute per square foot and we can convert it into another value, or another perspective. And so GPM per square foot, if we take that and we say, for example, cubic feet per second, and we divide that by square foot, then we actually end up with a foot per second, which is a velocity. So you can look at loading rates both as how much water we're putting on the surface and through a section of the filter, but it's also how fast is that water trying to move through the filter. And as we try to increase the speed, or we increase the amount of volume, we're also increasing the head loss. And then there's a relationship where we're falling off on the percent removal. So the idea is that if we slow the water down, then there's less chance for that particle to push through the filter. And so with all these ideas, we have media depth, we have media size, and then we also have the flow of rate. We're always trying to balance what's coming in and through that. And we're and that's kind of where the art of design comes into play. And we're trying to, as we try to optimize the filters given the space constraints or the footprints we have. And then we're also looking at the unit filter run volumes, this UFRV here on the side, that it's not looked at, from what I understand, much in the industry, but it's becoming more and more a useful tool to judge the performance of our filters. You know, we can do so much design, but we can also look at just doing pilot testing to determine what we want to do. There's a lot of things that can be determined through the pilot test. What kind of pre-treatment strategies we want to go to, how to control our flows, the depth of the media size and type, and this is all going to be unique to everybody's water quality, incoming water quality, as well as what we can monitor and those loading rates that we can push through the filter media that we're selecting. So pilot tests is always welcome, and it helps validate the assumptions that are made through calculation, and helps ensure that we're going to make the best process for you. And the ideas of water treatment and filters, I was told that you do everything you can beforehand to protect the filters, right? So because a filter is only effective with really kind of smaller particles. Otherwise, bigger particles are going to end up, or more NTU turbidity is going to end up reducing the efficiency of your filters. And so we wanted to look at pre-treatment. And so this is filtration kind of treatment is particle removal based on the surface chemistry, again, and not a straining or sieving process. So the untreated water can be difficult to filter. So we try to get the pre-treatment to change some of the chemistry so that it helps with the pre-treatments. And that can be done with coagulation, which is the changing of, we're actually trying to change the chemistry of the surface chemistry of the particle. And we use things like alum, ferric chloride, or even polymers. And then we move into steps for flocculation. So where we're taking a polymer and we're trying to grab onto the multiple particles and increase the size, the density of the particles that are in the water so that they settle easier. And then once we've created those flocks, that goes through the clarification process and trying to remove, again, trying to reduce the loading that goes into the filters. And then we can also add filter aids that increase the performance, again, trying to capture those particles even furthermore, and reduce the loads on the media. There's a couple rules of thumb that we follow if depending on what our influent water quality is. If we have high turbidities, typically greater than 5 NTUs, we're going to see these processes. We're going to include a rapid mix with your injections of your coagulants, your alums, your ferric, or other polymers, and then it's going to go through the flocculation process, clarification, and then on to the filtration. If we have something that's less than 5 NTU, we can typically go away. We have those smaller particles, and we can go through just the rapid mix and flocculation and let the filter really kind of capture more of that. But really what we're trying to shoot for is, when we go to look at what we can do on the filter, we always want to try and have a water quality of around 1 NTU or less. And if our influent quality is at that range of less than 1 NTU, we can just typically include our rapid mix, which would be maybe a pre-dose of chlorine or some of those filter aids before it goes into the filters. When it comes to control strategies of the filters, we can do several. There's several methods. They're all valid and useful, and whether we control the constant level. So that means that we're controlling the influent flow and we're keeping a constant level. But as our filter beds ripen, our head loss increases, and so we actually end up having to reduce the inflow to be able to and that reduces our output. That we can also do a variable level. So this is essentially letting the flow kind of be more constant, but we're allowing the filter bed to raise up. And as the filter bed raises due to the increased head loss as particles get deposited, then we can, once we reach level, then that triggers our backwash. Effluent control, again, we're just controlling what's coming out of the filter and maintaining those levels that way. There's also declining rates. Again, they're all useful. They're all used throughout the industry, and really there's just preference to what you want to do, how you want to control it. Filter sizes. So when we're talking about how big of a filter, a lot of the time it's based on what kind of footprint we can get out of it, as well as managing the rotations and productions. But we typically try to keep filters smaller, less than 1,200 square foot. I've seen them as small as 200 to 300 square feet. So there's quite a bit of range within that, but typically you don't see massive size filters. Again, it helps with operation and redundancy. Length, we keep lengths to widths of 2:1 to 4:1, and quantities, we want to make sure that the number of filters is going to be well below the approved loading rate and able to at least take one filter offline for backwash while meeting the plant capacity needs. There's also other plant specific criteria that's looked at that goes into sizing the filter. Filter media, there is different media out there, sizes, types, and the selection is based on the different factors. What is the prior experience of the design engineer, the operators, what is our treatment objective, and all these other items go into the idea of selecting what kind of filter media there is. We also look at, again, we talked about the diameter, and back in, when was it, about 1890s, Alan Hazen developed the idea of the effective size and the uniformity coefficient, which helps identify by keeping the diameters and the consistency of the media more uniform, that we can improve our filter quality. So I find it kind of funny that something that was developed more than 120 years ago is still used today and is still a valid thing. So so yeah, we look at the effective size, which we call the D10, or in other words, what is passing a certain sieve. 10% of that is below that weight, and then the uniformity coefficient is the D60 over the D10. So what is the 60th percentile of media grain in the diameter, or as compared to the media that's 10% of a certain grain size. We also look at the specific gravity, so how that is going, which affects how it settles. And we determine the grain sizes using the standard ASTM C136 sieve analysis for coarse and grain sand. And then we look at that grain distribution and we model the effective size and the uniform coefficient to be used. And we'll talk a little bit about what those sizes are and what we typically look for. When it comes to the media, we look at there are sand, anthracite, GAC, and sometimes even garnet that's used. And we look at what are we going to use in that process. And sand and GAC can be used, or even anthracite is a mono media, and it's just all the same media that's in there. We can divide it up because it helps with giving different bed depths and filter performance. Dual medias, you can have a layer of anthracite or GAC and typically over a layer of sand. Less common and older things that are used are a tri-media, which is a mix of anthracite or GAC over a layer of sand, and finally over a layer of garnet or ilmenite. And these are typically stratified based on the density of the particles, right? The anthracite or GAC is typically lighter than sand, and sand is lighter than garnet. We can find these filter material standards through AWWA B100 and B604, and so we can look at that further as well as other items. And as I said, that there are the uniformity coefficients and the effective sizes that we're looking at. And so here for anthracite coal, there's a range that we look for, and the depths that we typically find within dual media and mono media filters. We're typically in the range of like 1.6 to 1.7 for uniformity coefficients, with about a 1 millimeter in effective size for anthracite. Silica sand is we use a smaller particle, about a 0.5 millimeter plus or minus, with again a similar uniformity coefficient. Anthracite and coal gets a little bit, let's see, what was it? Granulated activated carbon is actually a little bit bigger of a particle in the 1.2 plus or minus range, with a uniformity up there again close to the 1.5, 1.6 range. But with a bigger filter or bigger medias, we typically end up getting a little bit thicker media depth, and especially for those monomedias. Let's see. Filter media compatibility relative to re-stratification upon backwash. Again, so what we're doing is when we're looking at these, we're trying to create we don't want an intermixing of our media, right? So we want stratification to let each material do what it's trying to do. And so with anthracite over sand, we want a D90 over D10 ratio of about 4:1 to 5:1. And then again, or when we're looking at the D10s, the anthracite is essentially about twice as big to the sand. Now in filter media depth, we've traditionally seen a historical depth of around 2 to 3 feet, and they're shallow filter boxes. But the current trend is that we're moving to deeper filter media beds of about 4 to 8 feet. I was looking up MOP 8, or not, excuse me, MOP 8, that's wastewater. I was Bulletin 10, which is Arizona's standard for design of filters and other water treatment facilities. And the deep filters that we'll get talking into here a little bit aren't as covered, but there is provisions for testing in there, pilot testing, to show what we want to do. So we'll talk a little bit about these, and I'll turn the time over to Lee to kind of carry on from here. Lee, are you on? I saw him popping in and out here.
I am. I'm here. Can you hear me all right?
Yes, I can.
All right, thanks. And I'll have you go ahead and flip to the next slide, if you will.
Okay.
So with media head loss, we'll get into a little more of evaluating your filters and how you can do that. But a couple of things to think about for your filters are, you want to know what the clean bed head loss is. So that's the amount of head that is in your filter just after backwashing when the filter's all clean. And then you have a terminal head loss or clogging head loss that is the point where you need to start backwashing again. So you can determine that in pilot tests, full-scale evaluations. But in general, we want that terminal head loss to be met before your particles break through. So go ahead and flip. Loading rates for surface water treatment plants have typically been, excuse me, 2 to 3 gallons per minute per square foot for granular media filters, but the current trend is really to go with higher filter loading rates of 6 to 10 and even higher gallons per minute per square foot loading rates, because we can get more capacity out of the same space, and water treatment plant costs are going up. So that's one area where we can get more efficiency out of the filter. And with the deeper bed, as Dane was talking about, we can still do a really good job of removing particles in those granular media filters. So typically we'll see some states have a maximum amount that they will let you or want to see a typical design. I think Dane included a bit from the Arizona bulletin there that says 2 to 6 gallons per minute per square foot. But if you want higher rates, they'll typically approve it if you can show that you can achieve it with a pilot test. Next, please. So these are some pilot tests of runs in Colorado. On the left-hand side is the unit filter run volume. So that's the gallons per square foot of filter media between backwashes. And different runs on the bottom from pilot test. And the color coding is different loading rates. So 5, 8, 10, and 11.4 gallons per minute per square foot. One of the things that we really look for in a good filter run is having at least 10,000 gallons per square foot. So a UFRV of 10,000 is an area where your filters are running pretty efficiently. And you can see you can achieve that at low loading rates and high loading rates alike. Go ahead and flip to the next one. These are the filter effluent turbidities that came out of each of those runs. So if you have a well-designed filter bed, and this was a deeper filter bed of 66 inches of anthracite, that you can achieve good filter effluent turbidities with a variety of different loading rates. And that's what you're looking for in pilot testing. Go ahead. So Dean was mentioning with the trend towards deeper filter boxes, deeper filters, higher filter loading rates, that these boxes can get pretty deep. So you have a filter media profile that might be 4 to 7 feet. You've got a couple feet of clean bed head loss that you have to account for in the filter. Some underdrains require media support gravels, which can be 2 feet, 18 inches, even higher in some cases. The trend is really to go away from support gravel and use underdrains that have media retention slots in them, so you don't need that gravel, but some still do. And then we also have to account for our expansion of the media bed, 20 to 30%. Backwash trough profile, 18 to 36 inches. And then we need our head loss allowance in the filter. So typically we want to see 8 to 10 feet of head available for our filter run before we see some breakthrough occurring. So we also need a couple feet of freeboard. So that means if we're building a new filter, it's really not uncommon to see filter boxes that are 25 to 30 feet deep these days. There are 3 general types of backwash. 1 is water-only backwash. 2, water with air scour, air and water backwash, and then a lot of older surface water filter, granular media filters have a surface wash on them. So hydraulic wash with a surface water agitator. So hydraulic only backwash, if you have a surface wash available, you would want to have a flow out of that surface wash, whether it's a rotating or fixed nozzle type that's 0.5 to 2 gallons a minute per square foot. You probably want to run that for a couple minutes before you start your backwash flow up through the bed, so you get the top of the media bed all disturbed and broken apart before you start your backwash. So then the hydraulic upflow backwash, want to see 20 to 30% bed expansion. We probably want to run at least 3 bed volumes through our filter. So if we calculate how many cubic foot of media we have in our filter and then convert that to gallons, then that's how many gallons our total backwash flow should be. We want to continue the surface wash for the first 3 to 4 minutes, and then we'll finish up with water only, surface water off, to let the media get back in place at the end of the backwash. With air and water backwashing, we would design our air scour between 2 and 5 standard cubic feet per minute per square foot. We want to run it for 1 to 2 minutes at the start of our filter before backwashing. Then we want a little bit of simultaneous air and wash water with the air running and water at about 20 to 50, 25 to 50% of our total flow. And then we turn off the air and we finish up with backwash only so we can stratify the bed after it's been cleaned. In general, we use less water for this, but you still need to be able to expand the filter bed to get proper stratification. So just a reminder that that water is more dense when it's cold. So you can get more bed expansion in cold water at the same flow rate that you can when the water warms up. So if you're in a place where your surface water is mixing between groundwater and surface water, or if you see seasonal changes in your temperature, you want to account for that in your backwash. And again, you may have 20 or 30% bed expansion when the water temperature is cold, but in the summertime, that same rate may give you less of a filter expansion. So you need to generally increase your filter backwash rate when the water temperature gets warm. And I used to operate a water treatment plant for 5 years. We changed our flow rates almost weekly because our temperatures in the river were changing very frequently. So it makes a difference in keeping your filters clean. Surface wash, I mentioned before, most of them are rotary. The water pressure rotates the surface wash around the filter. It scours the media surface prior to the backwash, gives you a little bit of agitation below the media. Typically, they're placed 2 inches above the media and spray into the filter bed itself. They typically have dead zones in the corner, so if you have a filter with a surface wash on it, typically the operator has a hose and they have to break up the corner area to make sure they're getting good backwash. So that's always something to check and make sure you're doing every time you backwash. Air scour provides a really effective agitation, reduces the amount of wash water we need. Typically, rotary bulb blowers are used. There's variable head that they have to operate against, and we generally use stainless steel piping, so it's not cheap, but it does cut back on the water. Backwash troughs, we space them uniformly throughout the filter. They need to be high enough above the filter bed that you can expand the bed and not get media carrying over into the trough. They're typically made out of fiberglass or concrete, and they have information about loading for available from the manufacturers. So just a little sketch of where the bottom of the backwash trough needs to be inside your filter. You've got your media, and then when you are backwashing, you got to account for 20 to 30% of that, and the top of that expanded media bed needs to be about 6 inches below the bottom of the backwash trough, because if it gets into the backwash trough, the velocity right around the trough increases and it'll carry the media right up over the top. So you want to expand the bed so that it doesn't intersect the backwash trough. Under drains are there to support the media, collect filtered water, distribute backwash flow and air as well. Historically, seen a lot of nozzle plenum type of under drains and block under drains like Leopold blocks. Now we're seeing a lot more lateral pipes, typically stainless steel, that lay on the bottom and are media retentive under drains, so that they have a very low profile, and you can get more out of your filter box. Just a picture of a nozzle plenum on the left. They limit the amount of flow that comes up through each nozzle. It's critical to have a good nozzle design, and unfortunately, you have to get in there and replace them periodically. On the right, it's a typical Leopold filter block. So old blocks, you put support gravel on top of them. Then they went to an IMS cap on them, and now they have filter retaining slots that are put on the top of them to really help. But the IMS caps were getting a lot of head loss built up in biologically active filters, so the retaining slots do a better job of preventing that. So the underdrains are underneath your filter, sand and gravel, and anthracite are on top of that. It's good to know from the top of your filter box down to the top of your filter media, what's that level supposed to be, so that you can at least once a year go in and measure to the top of the media bed, not just to see if you're losing media, but also if there are spots in your filter bed that are too low or too high. If you see mounding or divots in the filter media bed, it could mean that you're not backwashing properly, or you have a broken underdrain or a clogged underdrain. So it's a really simple thing to do, be able to measure down to the top of your media bed with the tape measure, and you do it in many different spots in each filter. And it can absolutely be a critical way to determine the health of your filter. So that's a very simple thing we can do to keep tabs on how our filter is performing. So granular media filtration, Dane talked a lot about the design. It's a really versatile treatment process. We know it can do a great job at turbidity removal, particle removal, pathogen removal. The trend has been to operate more granular filters as biologically active. So we get some removal of dissolved organic material in that filter as well. Whether or not you have ozone in front of it, which enhances the biological growth, but even without that, you can see some real benefits of running the filter biologically. So there's lots of vendors, lots of options for granular media filtration, and most of the large new plants that are built in the last 10 years are all granular media filters. They're not membrane plants. So it's still a very popular and worthy technology for water treatment. All right, go ahead, Dane. Sorry.
No worries.
So Dane talked about the different filter loading rates and tracking this unit filter run volume. It's kind of a critical thing to be able to see how your filter is performing. I know as an operator, we always looked at our filter run times, but it's really not as meaningful if you have different filter rates that you're running. So if your plant's only running at half capacity, You may have a filter loading rate of 2 gallons a minute per square foot. And if you get a 40-hour runtime, that might only be a unit filter run volume of 4,000. That's not a very efficient filter run. On the opposite side, if you're running 8 gallons a minute per square foot and you get a 24-hour filter run, that's a pretty efficient run. So you need to know how many gallons are passing through each square foot of filter between your backwashes. That's the unit filter run volume, and that's a really good measure of performance for filters. So this just shows a percent of water loss in a filter versus the unit filter run volume from backwashing and filter to waste. So you can see the higher you get on filter unit run volume, the less percent of water you're wasting. And 10,000 gets you down to about 3%, and higher is better. So that's a goal we're trying to get to for most surface water treatment plants. Next one, please. So why do we want to optimize our filters? We just talked about, having a good efficient filter, 95 to 97% for a 20 MGD plant. That saves about $300,000 a year. So in addition to having a well-run treatment plant that protects public health and is good for customer acceptance, you're also saving money for the plant. Filter optimization techniques include optimizing pretreatment. We'll talk a little bit about that. Trying to get our filter runs so they terminate on head loss, not turbidity breakthrough. And we'll talk about ways to do that. Optimizing filter backwash procedures, making sure we're not backwashing too long or too short. And then filter to waste procedures as well. Filter ripening, if it's too long, it's contributing to our waste out of the filter. So there's a number of things we can do. Key to good filter optimization includes maintenance at least once per quarter. You should look at your filter run profiles, see what you are backwashing on. Hopefully it's terminal head loss and not turbidity breakthrough or particle breakthrough. You should look at your unit filter run volume periodically and see, are we getting 10,000 gallons per square foot between our backwashes? You want to check your media expansion. There's a little tool you can build yourself or buy, and it's very simple to look at your media expansion without interrupting your normal operating procedures. So that's a great thing to have and know how to use it. If you see temperature swings in your surface water, you should be adjusting that for flow, at least on a quarterly basis. And then want to check your backwash duration and see, are we backwashing too short or too long? And we want to check our media depth. So we talked about going into the filter. You can stand in the troughs. You can measure from the trough. You can measure from the filter wall, but getting measurements from multiple spots within a filter down to the top of the media bed is critical. Then you can start to see if you've got some divots or mounding occurring in the filter. Once per year, you should do a filter core, look at solids retention on your filter media, and this is right after backwashing. You want to do that, and then we also can periodically look at a sieve analysis to see if the effective size or uniformity coefficient on our filter has changed. We need to maybe add media periodically, and you should do that, but you should also try to figure out why it's being lost. So we talked about ideal filter runs. That is where our head loss builds up to our terminal point before we start to see our turbidity and particles break through. That's really what we want to do. And if that isn't happening, then we want to look at potential causes and think about different ways we could fix that. So if we have a long ripening time where more than 15 minutes it takes for filter to waste, maybe our media is over cleaned, maybe our influent solids are too low. We might want to reduce our backwash duration. We might want to look at a filter aid, and we may look at what our clarification performance is as well. If we have a premature breakthrough of the filter media, we could have an under-cleaned filter. We could have not very good particle media charge neutralization, so that they're holding each other apart. Or maybe we see quick filter flow changes that are causing breakthrough. So we want to increase filter backwashing potentially. We want to look at adding a filter aid and minimizing flow changes on filters to the degree that you can. Third, if you see rapid head loss, sorry, Dane, if you see rapid head loss building up, media might be under clean, you might have high solids coming in. Typically, of a clarifier, we want to have 1 NTU or lower. 1 to 3 is kind of common, but ideally you want to have less than 1 NTU coming off your clarifiers. And then we may have too much filter aid feed as well that can cause head loss to build up. Typical filter aid polymer doses are like 0.01 to 0.02 milligrams per liter, just a tiny, tiny bit of filter aid polymer. Go ahead. So tracking UFRVs can help identify trends that are allowing optimization. Look at your filters, seeing if you get to that 10,000 goal. Go ahead. If you have pilot filter columns in your plant, you can look at some changes to filter aid dose. You can look at changes to your backwash procedure and see if that gives you some optimization. The feed for your pilot filter should be off your clarifier so that you're getting the same type of water that you see in your larger filters. Typically with backwash, if we have water-only backwash, we want to see 20 to 25% overall bed expansion occurring. With air and water, based on the size of the particles, there should be a minimum fluidization velocity that you calculate based on the 90 percentile of the media size. So it's typically around 6 to 8 gallons per minute per square foot. And then you got to finish up that air water backwash with a water only backwash that should be back to the 20 to 25% expansion. Different states have different requirements. So in Utah, for example, you have to provide at least 20 gallons per minute per square foot or 50% bed expansion. You don't have to operate it that way, but you have to design in that amount. And Arizona, they list up 20 to 50% bed expansion. Again, I mean, it's a good idea to have some extra backwash capacity, but over expanding, over cleaning your bed is a real issue as well. I see lots of filters that are too clean, and we'll talk about that. So we talked about cold water expands media for a given backwash. If you have a 20-degree water compared to 25. So most of these charts are at 25 degrees C. If you have 20 degrees C, you only should be backwashing at 91% of the design rate. If you have 30-degree water, you need about 109% of the design flow rate. So good thing to be checking for your plan. Okay, we talked about backwash expansion. There's a little tool you can buy or you can make. I've made lots of these. You just cut some PVC, set them right next to each other, and they're in different inch increments. So I typically do 2, 4, 6, 8, 10, 12 inches, and there'll be a long pole on it. You set it down on the surface of the bed before you start a backwash. You do your normal backwash, hold it in place, and then when you're all done, you pull it out and you see which of the tubes has been filled with media, and it tells you exactly how much your filter bed is expanding. It's quick, it's simple, it's inexpensive, and it gives you a good feel for whether or not you're getting good expansion of your bed. So you can put this expansion tool down on the top of the media bed. It'll sit there. You got to kind of hold it in place. But then when you're done backwashing, you just lift it out. You look and see which of your pipes have been filled with media. I know that picture is hard to see up in the upper right-hand corner, but about the first, I don't know, 4 or 5 pipes have anthracite sitting in them. That's what you're going to see. So you'll know right away that my filter bed expanded 8 or 10 inches based on your tool there. So you can, if you've got SCADA in your plant and variable feed for your backwash, you can plug that into your SCADA. It'll look at the water temperature and adjust it for you. More typical, you don't have that capability, so just be aware if your temperature of your water is changing, you need to adjust your backwash rate. How long should backwash occur? So too much or too little is very common. Typically, it's not hard to figure out how long. You go in and just take turbidity samples at 1 or 2 minute intervals throughout your backwash, and then plot the results on a piece of paper and record, your data, what your flow rates are, all that good stuff. Go ahead and click one. So what we're typically looking for when you plot that data is you're going to see the turbidity spike up over 100, maybe 200, 300 in some cases, depending on how dirty your bed is, and then it'll come down slowly over time throughout the backwash. You want to backwash until your turbidity hits about 10 NTU. You don't want, I see lots and lots of filters that are backwashed down to 1 or 2 NTU, and it's not just a waste of water, it makes it hard to start the next filter run as well because it takes longer for that filter to ripen. So you want to backwash till you've hit about 10 NTU, and then you're done. You can do a core sample to look at solids retention on your filter media. It's very simple to do. There's coring tools. You can go in, take a core of your sample after you dewater, or out your filter bed after you dewatered it. You divide it up into different areas, and then look at. You take a 50-gram sample at each area of your filter, and you wash it in 5 successive 100 ml washes of water, and then you take that and read the turbidity of it, and it'll tell you how much solids you're retaining on the filter. So you want to do this right after backwashing. and see if you're getting your filters clean. Go ahead. If you're less than 30 NTU, you backwash your waters too much. So if you're 30 to 60, that's the target for what we want to keep the amount of solids, the flock in our filters after backwashing. And if we're 60 to 120 or higher, we've got a bed that's not getting cleaned up enough. So coring a sample, doing that flock retention analysis is a really good troubleshooting guide for filters. So you can plot the solids retention time. You can see if you have an issue with the deeper media, the media on top, and do some troubleshooting based on that. Media conditions are key to performance. So once a year, at least, you should go in and look at the size of your media. That same core sample you can send to a lab. They'll do a sieve analysis of it, and you can calculate your effective size and uniformity coefficient. Go ahead and click. So go ahead and do that again. If you're losing more than 5% media per year, you should look into why that's occurring as well. We're almost out of time, Dane, so hey, perfect. An hour's worth of talking. If you have questions, I'm sure Dane or I'd be happy to answer them. And there is an AWWA guide on filter evaluations. That's a good tool. AWWA doesn't like to share their stuff, so we don't have it in the handouts, but it is available on their website, and it's a nice step-by-step approach to doing the filter evaluations.
Yeah, it looks like it was linked in the chat.
Yep, that's just the table of contents, but
Thank you very much.
You can see what's in there.
That's good. If anyone is interested in this guide, please email azopsert@azdeq.gov. We'll go ahead and send you a link to this guide as well. We are at 11, but we did have one question. If we could go ahead and squeeze that in real quick.
Yeah.
This one came from Neil. Oh, excuse me. Yes, this is from Neil. With polymetric filtration materials, is there a concern about the introduction of microplastics into the water stream?
That is a really good question. I would say that, yeah, potentially there are microplastics that can get into the water stream with all of the chemical production that we're doing. Polymers are very long chain organisms, but in a surface water treatment plant, the potential for microplastics is already in the surface water. I mean, we're seeing them in rainfall all over the world. So it's the potential for microplastics is an issue that the whole industry is going to be dealing with, kind of like we're doing with PFAS right now. Great question though.
Very good question. Thank you very much, Neil. So we're going to go ahead and move on. Please, if you want to take a screenshot of Lee and Dane's contact information, if you have follow-up questions, please do so. We will also have their email at the end of this presentation for everyone to take as well. Once again, thank you very much, gentlemen, for attending or for presenting today.
Thank you.
All right, thank you.
So it looks like next up we have still tank maintenance and inspection. Alex, are you available? Looks like he's getting his mic ready. Let's go. Alex, are you able to hear me okay? Don't in here. We'll go ahead and give Alex a couple of seconds to set up. But just in case anyone did need.
Hello?
Oh, perfect. All right,
Can you hear
Alex,
me?
I can hear you just fine. I'm going to go ahead and send screen power to you.
Okay.
I'm going to do this.
Alrighty.
Everything looks good.
Perfect. Thank you. Hello, everyone. Welcome. If you guys could just bear with me, I'm fighting probably the worst cold of my life right now. But my name's Alex Valencia. I'm an inspector with the Arizona Department of Environmental Quality, and today we're going to be going over maintenance and inspections on steel storage tanks. Two main purposes from this presentation is to extend your service life of your steel storage tanks, and as well as continue serving healthy and safe drinking water to your customers. This is just a rough overview of what we'll be going over today. We're going to be going over the major components of steel storage tanks, the types of inspections, and some maintenance tips that you guys could integrate into your maintenance plan. Additionally, we also have some resources, and we'll have time for questions at the end. So the first thing that you guys will notice about a storage tank is going to be its body. Typically, it's going to be made out of steel in this case. There are going to be seams either welded on, or you're going to see rivets on there. It's supposed to have a watertight roof, and its shape is usually cylindrical, although I've seen like some square or cube looking plastic storage tanks. It's normal for a little bit of bulge in the storage tank. However, if it starts to look excessive, then it may be some cause for concern. The interior of the tanks, typically these will have liners. These liners will help prevent the inside of your tank from running into any issues, helping discourage any kind of interaction between the water and the actual steel, as well as helping extend the service life of your tank. A lot of systems like to utilize gauges inside the interior of the storage tanks. These gauges help monitor water levels, temperatures, or whatever they may need it for. These liners are supposed to be leak proof and help prevent the amount of leaks that you may deal with. The interiors of these storage tanks also typically should have some form of chlorine residual. This is to help prevent water from becoming stagnant, as well as cathodic protection. This is very similar to what you'll find in your hot water heater at home. Basically, there'll be a sacrificial, anode rod or something of that sort, and basically something is going to get corroded, so might as well have it be a piece of steel rather than the steel on your tank. For the slab or foundation, these are typically going to be concrete or a metal ring with drainage fill. This actually seems to be one of the more common issues that we run into during our actual inspections. There'll usually be debris or trash on top of the slabs, or the rings and the lips will be completely covered in debris. When these are covered in debris, it actually can cause issues for the public water systems, because they're not able to detect leaks early on before they actually become a bigger problem. You want to have the area around it graded. So essentially, if you're pouring water out of a water bottle, you're going to want to make sure that it's running away from the storage tank, so you're not having issues where water is going to start pooling underneath your storage tank. There are liners available. These are very rare, but these are meant to extend the service life. Basically, it looks like a little piece of felt, and it'll actually go between the concrete slab and your actual storage tank. The gravel material underneath your storage tank should allow for proper drainage. This is going to help prevent water from kind of building up underneath your storage tank. If you don't have this kind of gravel material underneath, then you may run into this issue where water will start to actually collect inside the soil, and could actually lead to severe corrosion underneath your storage tank, or actually even displacement if the soil underneath is susceptible to expansion from water. You want to ensure that there's no damage done to the slab or the foundation. If there's minor cracks, then feel free to fill them in with an NSF grade sealant, but any major cracks are going to require more than likely replacement of the slab. You want to ensure as well that your slab is reinforced and strengthened. This is typically done using rebar or any other construction grade materials that your contractor may utilize. Vents are needed to help prevent vacuum. These vents are supposed to be protected with the number 16 wire mesh. That is supposed to be non-corrodable, but lately I've run into the issue where the wire meshes that some public water systems will utilize are actually much bigger in terms of they actually allow a lot of bugs and critters to get in. So you want to ensure that it is a number 16 wire mesh. This is not only going to help prevent your water from having any kind of biological contamination, but it's going to help your the inside actually breathe, so to speak, with the vacuum issue. You want to ensure that your vents are serviceable, that they're attached securely to your tank, and you're going to want to have one of two types. You want to have the hood or a vent that's turned down, and the reason for this is if it begins to rain or if it's storming, you want to ensure that you're not getting any rainwater or anything that may cause contamination inside your finished potable water. One big issue that we do run into is that people will automatically assume a vent can also serve as an overflow. That is not the case. So ensure that you have both a vent and an overflow on your storage tank. Hatches are a very integral part of your storage tank. They allow you to check the conditions of the interior. We want to ensure that these hatches are securable, whether that's through a lock or any other means. You want to ensure that there's a gasket or a seal on it. So we do not want metal on metal. You want to ensure that there's a seal or a gasket. This is going to ensure that there's a watertight, airtight seal around there. This helps prevent contamination. And we want to ensure that this gasket or seal is also serviceable, especially for the hatches that are located closer to or below the water line. These are going to help prevent leaks from occurring. A lot of times you guys are actually able to see the condition of the gaskets, usually towards the bottom of the storage tank on those secondary hatches, just by looking at the exposed plastic material. Usually on those types of hatches, you could actually see some of the gasket material actually squeezed out around the edges. And depending on how dry rotted it is, it can kind of give you an idea of the condition of the gasket. Placards. Placards are actually going to be very helpful come inspection time with ADEQ. So we all know that everything needs to get permitted properly, but prior to permitting becoming a thing, a lot of components were installed without the usage of permitting. So these placards tend to come in real handy when we want to grandfather in a storage tank. Say a storage tank was put in the 80s. Back in the 80s, permitting wasn't required. So this will actually help save you from having to get a permit. And this serves as the evidence that the storage tank was installed before permitting was required. But additionally, these placards help provide some other useful information, such as the capacity, the model number, or a serial number in case you guys need to buy any parts from the manufacturer or conduct any kind of repairs. For the water lines, we want to ensure that any water lines associated with the storage tank are leak-free. They have a purpose and they're simple. While this picture that we have here on the screen, I understand it's a plastic storage tank, but I wanted to use it as an example. There was a water line that was coming up from the top, leading down to the distribution line at the bottom, and the distribution line at the bottom was already connected to the bottom of the storage tank. So essentially the water line running over the top was served no purpose and was leaking. So you just want to keep your water line simple. You want to know where your lines are located, especially if you need to conduct repairs, and you want to ensure that you guys have the correct valves. And yeah, like I said, don't be like the picture. Overflows. Overflows are not going to serve the same purpose as your vents. These overflows are needed to protect your tank. We want to make sure that they're air gapped in case that there is a loss of pressure. We don't want to have any kind of cross connection situation. We want to make sure that they're screened so that bugs or small animals can't get inside your storage tank. And we want to ensure that there's proper drainage away from the storage tank and your slab. So if for whatever reason water is coming out of your overflow, it's not going to start pooling underneath your storage tank and lead to bigger problems down the road. These overflows are actually going to help prevent pressure from building up inside your storage tank. So say for whatever reason you're getting too much water in your storage tank, it's going to help remove some of that excess water and prevent the tank from bulging, as we tend to see in some of the older storage tanks. Gauges are typically found across different storage tanks. These can serve different purposes. I've seen electronic gauges. I've seen the bobber gauges, which basically just float along the top of the water line. These gauges help provide useful information, again, such as temperature, water level, and any other water quality parameters that may be pertinent to the public water system. So if you guys all look at the picture here where we have the water level gauge, so we all know that there's a guide wire that actually goes inside the towards the inside of the storage tank. A lot of people tend to not pay attention to this, but there's actually an opening that's fairly large. So what we recommend doing is you want to get a number 16 wire mesh, cut a slit down to the center of it, and wrap it around the guide wire, or purchase a commercially available grommet and wrap it around the guide wire, and essentially close up that gap that introduces the guide wire to the inside of the storage tank for your exterior water gauges. For your ladders and your safety equipment, these are meant to prevent accidents, as well as prevent any kind of unauthorized access. These ladders tend to have the little connector for like a lock to help prevent, unauthorized personnel from accessing the top of the storage tank. This can help prevent any kind of trespassers from introducing contaminants into your storage. No, my apologies. Whenever you guys are utilizing your ladders, you want to ensure that you guys are using a harness and any other proper PPE or safety equipment. You want to plan ahead. Inspectors are no longer climbing the tank, so when it does come time for your ADEQ inspection, you want to make sure that someone has been able to reach the top of your storage tank, has taken pictures to provide the inspector with. I know that some water systems may not have a ladder, or they may require a commercial service to access the top of their storage tank. So just start to plan ahead. If you need to, budget for a commercial service or equipment to access the top of your storage tank. And you want to ensure, again, that it's secured when not in use. For the ladders that are not lockable, which are actually very rare, you typically tend to see graffiti or signs of trespassers on the tops of the storage tanks. You'll see spray painted figures or trash on top of the storage tank. So again, we want to deter that by locking all our ladders and restricting access. And this actually leads into our surroundings. For your surroundings, you want to maintain your landscape. You want to keep away from your tank trash, debris, flora such as bushes, trees, and you want to keep septic tanks and livestock at least 100 feet away from your storage tank. Very often will I come across like tree branches touching a storage tank. That's a big no-no. That could cause problems down the road. And I understand that a lot of storage tanks are in like very remote areas that are somewhat difficult to access. So what we always recommend is for a public water system to come up with a maintenance schedule, a landscaping schedule to help facilitate proper landscaping. And for your security, again, fencing, locks, other security measures such as signage, we want to restrict access because, you know, teenagers or any other trespassers could potentially get into your facility. They could contaminate your water. They could cause serious damage to a lot of expensive equipment. And at the end of the day, you know, we want to ensure that we're providing healthy and safe drinking water to our customers. So that leads us into our types of inspections. So one type of inspection that a lot of public water systems will deal with are your comprehensive inspections. So these are commercially available inspection services. These are actually a great time to get your repairs done, get cleanings done. For a lot of these comprehensive inspections, the interior is the focus. This is usually when the public water system will have a diver go inside the storage tank if they don't want to drain it, and they want to have the inside inspected, the liner inspected. Now, these can be very pricey. I did speak to a diver, and essentially they're going to charge quite a bit just to have someone go in there and inspect the inside. So it's going to be a matter of having to pay a diver a lot of money or having to drain your storage tank. For this kind of situation, if you guys just plan ahead, especially if you have multiple storage tanks, then you guys could just drain one tank at a time. Your next kind of inspection is going to be your sanitary survey. This is your drinking water inspection. This is when you guys get to have fun with ADEQ. For these public water inspections, there's 4 components to them. There's going to be health, safety, cleanliness, and proper supply. So we want to ensure that you guys are serving healthy and safe drinking water, and that you guys have ample supply should there be any kind of disruption, or so that the public water system is able to meet its peak demand. So some of the items that you should self-inspect regularly are going to be your tanks, sources, treatment, and paperwork, to name a few. If you guys have had an inspection recently, you guys know that we send you a pre-inspection email. This pre-inspection email is going to have a checklist of items that not only do we check during each inspection, but that should be checked by the owner or operator at least monthly. And specifically for your tank, you want to ensure that it's serviceable, it's under sanitary conditions, you have sufficient storage to meet your peak demand, and that it's code compliant. Third type of inspection are your self-inspections. Again, we spoke a little bit about this. A lot of public water systems may not know that it's always their responsibility at the end of the day for you know, their goal of serving healthy and safe drinking water and maintaining their proper maintenance and operations of their system components. If a public water system may not have much of an idea on how exactly to conduct a self-inspection, ADEQ can provide resources, so feel free to reach out to your local CAC, your community-based liaison, or you know, your inspectors. We can provide you with materials, resources, and essentially show you guys how to do a proper self-inspection. And again, you want to, for your tanks, you want to ensure that they're serviceable, sanitary, they have sufficient storage, and they're code compliant. And at the end of the day, the inspections are always going to be your responsibility. For the smaller public water systems, an issue that we tend to run into a lot is that the public water system owners will think that the entire responsibility falls under the operator, but at the end of the day, it's the actual public water system itself that's responsible for any kind of violations and ensuring proper maintenance and operations. This leads us into our maintenance tips. So the most important part of having proper maintenance is planning. For planning, we want to make sure that we're planning ahead. The tanks, we want to ensure that they're located in proper areas. So we want to ensure that they're not located near any kind of livestock or septic tanks, that they're in a clear area where they're not going to basically end up like this picture. We want to ensure that they're installed properly. Replacement parts, that's a big one. So I know it's mentioned in your EOP critical or your emergency operations plan for critical replacement parts. We all know that things are going to break down eventually, so we want to plan ahead. So your leaks can occur anywhere on the tank. I mainly tend to see them on the main body. Unfortunately, a lot of public water systems, they tend to not address leaks until they become a bigger problem. So the sooner that you guys are able to address your leaks, the cheaper it'll be for the public water system, and the lower the impact it'll have to the water quality. So some of the fixes that you guys could do on these leaks, they do have NSF grade sealants for some of the more minor leaks or patchwork from welding. If you guys start to have anything larger than that, then panel replacement may become an option. Paint is another integral part of your maintenance. Helps improve the look of the tank, and it actually helps protect the steel. It may reflect some of the heat, and paint is a great indicator of stress points and hot spots. If you guys tend to have a specific area where the paint is starting to fade or starting to corrode, then that could provide some insight into a bigger problem lying underneath. Keeping your tanks freshly painted using approved paints helps identify problems before they become an even bigger issue. A lot of water systems can make a schedule where they plan to paint their storage tank every 5 years, every 10 years. It's not cheap, so budgeting ahead is always a good option. And you just don't just paint over an area that's corroded or damaged. You want to ensure that you look for the root cause, as well as treat the area, whether that's getting out a wire brush and busting rust. Landscaping, again, landscaping's one of the more common violations that we have. Flora should not be touching the tanks. So you want to have the area around your storage tanks cleared out. You don't want to have tree branches touching or have excess landscaping around the area. This could invite animals, critters. One issue that we do tend to see is that storage tanks will be on the edge of a property that borders with another private individual. This individual may have, trees that are going over the property line and actually touching the storage tanks. So again, this leads to planning, proper planning, setting a schedule, identifying those kinds of issues where maybe you may have to speak to the neighboring property about, getting your equipment over there to ensure that there's proper landscaping around your storage tank. And excess growth can hint towards leaks. So if you notice that you have a fairly empty field, but on one side of the tank there's trees or not trees, small bushes or small plants growing out of the slab, then that could hint towards a leak occurring at somewhere in the vicinity. Slabs and foundations. So for your slabs, you want to make sure that they're free of cracks, chips, or corrosion. Again, for some of the smaller issues, NSF grade sealants work wonders. This picture right here kind of helps depict the situation that we don't want to see. There's, rocks, debris, grass growing over the lips, growing over the rings. We want to ensure that the lips and the rings are always exposed, as well as, this public water system here was just tossing trash behind your storage tanks. I believe that's an old check valve that they just had sitting there. I've seen hot water heaters and all sorts of debris just leaned up against the tanks. You guys don't want to do that. Having the area clear of debris helps, again, identify any potential leaks that may be occurring, as well as help, discourage animals from getting anywhere near the storage tank. And again, you want to ensure that there's proper drainage directed away from the storage tank and other major system components. For your inspections and your relining, again, this is a great opportunity to identify some problems before they become a bigger problem. Usually during your comprehensive inspections, the entirety of the tank should be inspected for any kind of leaks, signs of corrosion, and this is going to be a perfect opportunity to, again, conduct your repairs. Liners as well, if you guys can budget for the liners, they help protect the tank and keep the water supply safe. So it is something that we highly recommend. And again, for your disinfection and your residual, we want to ensure that there's some kind of chlorine residual in the storage water. This helps prevent stagnation, especially if you're a public water system where it may be borderline to being considered seasonal. So you're not having a lot of water moving in and out of those storage tanks. Again, chlorine is corrosive, so this is something that could be combated with cathodic protection. And maintaining this residual can help protect the distribution lines from bacterial growth. And these steel tanks tend to have vents for vents, so this could actually introduce airborne contaminants. So you want to ensure that you guys are preventing as much contamination from occurring. And know your breakthrough chlorine levels. A lot of public water systems may not know how much to chlorinate, so they may be over or under chlorinating. For your water chemistry, you want to ensure that it's balanced to keep your supply safe and palatable. A balanced water chemistry as well. It'll help protect your equipment. And the chemistry in your tanks may actually differ from the distribution due to like settling, stagnation, and precipitates forming inside the storage tank. So you want to cycle your water as well, especially if your tanks aren't being used as much. Pretty similar to what you have in your hot water heater at home, where you find sediment building up in the inside, especially if it hasn't been used in a long time. And one little tip, if you're a public water system that might be in an area where freezing tends to occur, you want to vary your fill levels. So the water line, you want to change it. This will help water from freezing over inside the storage tank. And again, flushing, right? Flushing will help possible contamination, or it'll help if there's possible contamination. It'll help prevent stagnant water and should be done whenever extensive repairs are conducted. So some protective devices and measures, vents. These vents help protect against vacuuming and bulging. The air gap helps protect against contamination. Backflow devices, again, help prevent contamination, especially if you have like a fire protection system. Cathodic protection helps prevent against corrosion, and cycling your water levels helps prevent stagnation and precipitates. And here are some resources that I've come across that may actually serve some utility. So of course we have our ADEQ drinking water webpage. This is where you can find a lot of the materials that were used to create this slideshow today. So you can find information on permitting or information on your CAC, changes to rules. But this second link right here, the NSF approved materials and vendors. So this is actually something that I came across quite recently and I thought was very useful. So NSF actually has their own search engine, almost like a Google of sorts, where you could look for a particular component and it'll actually provide you a list of all the approved vendors that sell that specific component. So this is something very useful if you guys need to replace something and you want to ensure that everything is NSF approved. Here's some contact information. Again, you know, if you guys are conducting self-inspections or just want to take a look at maybe your maintenance schedule, feel free to reach out to me and I could provide some resources and potentially some guidance. Alrighty. Oh, I guess the last one didn't work. Are there any questions?
Yes, actually, we have quite a few. Thank you so much, Alex.
Yeah.
It's really informative. So let's go ahead and start with David West. Looks like a question here. Are there recommendation or guidelines for what percentage tank water levels should drop on a daily basis or other time frames?
I'm sorry, can you repeat that?
Yeah, are there recommendations or guidelines for the percentage of water, tank water level can drop on a daily or other time frame basis?
So I'm assuming he's asking about the drop in water level during peak demand. Is that what you're
If you
hinting
can
at?
clarify, David, um, is this for peak demand, off season?
And
While
yeah,
he's
go ahead.
clarifying further, oh, okay, so it looks like both peak and seasonal, off season, excuse me.
Okay, yeah. So there is a guideline on that. If you reach out to me here, I could provide you some more specifics, David.
Okay, perfect. Thank you very much, David, for the question. And this one's from Al. Why do I need to use an NSF sealant on the concrete slab if it has no contact with the water?
So again, my apologies. That might have been a typo. So you want to ensure that you guys are using an NSF sealant on the actual storage tank. Basically, a good rule of thumb is if it's making direct contact with the water, NSF ANSI approved. But for your slab, yeah, if you want to ensure that you guys are just utilizing a proper sealant for it.
Perfect. Thank you, Alex. Next one's from Brian. All right, you might get a kick out of this. Why do the ADQ inspectors no longer climb storage tanks? You guys are great at helping utilities keep vent screens replaced as needed.
Well, for that, I suppose it's more of a safety issue. I do know some of the inspectors actually enjoy climbing the storage tanks, but yeah, unfortunately, we can't do that anymore. And you know, we do know that some of the storage tanks that we do run into, especially for the real tall ones, they may require, you know, commercially available services to reach them. So it's again, it's just a matter of safety and potentially liability.
Perfect. All right, we have another one from Andrew here. If we install a cathodic protection system on a storage tank, does that eliminate the need of recoating the interior of the tank? Are cathodic protection systems cost effective over the life cycle of the tank?
Yeah, so cathodic protection can actually, you know, extend the service life of the tank and as well as the liners. Um, it may not completely remove the need for relining your tank, but it'll at least extend the service life of it significantly. From what I've spoken to from public water systems, the cathodic protection is extremely cost effective and will actually end up saving them money down the road.
Perfect. And from Teresa, excuse me, does your small water tank need to be painted?
So Teresa's asking if a small water tank needs to be painted.
Is this in regards to a sale? To Teresa, if you can further explain. Also, they're getting that comment, clarifying that question. Brian does say, way to go, and he hopes you feel better.
Oh, thank you.
Okay. So I may have missed that earlier. If Teresa's still on the line, if you want to clarify the question. Okay. She has a small steel tank. That's why she's asking if it needs to be painted.
Okay. How small are we talking here, capacity wise?
If you have the gallons. Looks like 1,500.
Okay, 1,500. Yeah, I would still recommend painting it. Obviously with the tank that's small, more than likely shouldn't need to be painted as often. But again, it'll help protect the main body of the storage tank from corrosion. And again, it'll help identify any problems down the road. If there's any kind of small leaks, then you may potentially actually see like the paint running a little bit. Or if there's any kind of corrosion that's occurring underneath, you'll see the paint will start to kind of chip off or kind of bubble underneath. So it is recommended, even for a tank as small as 1,500 gallons.
All right. Perfect. Thank you so much, Alex, for your time. It's really informative. Alex's information here is on the screen, in front of you, phone number and email if you have further questions. It looks like we're wrapping up a bit early, but I did want to launch one quick poll. Alex, do you have any parting words or any information you'd like to leave?
I do not really. Just if you guys have any more questions, I'd love for you guys to reach out to me, and hopefully I can provide you guys with some more resources.
Perfect. Thank you so much, Alex. So here we go. We're going to launch this poll here. We've got quite a lineup of in-person events for OPCERT certification outreach next year and workshops, including math, leadership development, cybersecurity, distribution workshop. But I am interested to see how many more people what other topics people would like to see for webinars. We'd like to save more broader topics for webinars since we can reach a broader audience across Arizona. And potentially out of state. So if you can fill out this poll, that'd be excellent for us. Also, I'll go ahead and share the screen here. I'll change presenters to myself as well. All right, looks like we got a slowdown on the poll, so I'll go ahead and close this. I'll go ahead and launch it too. We'll go ahead and share those results with you all. So right now it looks like there's a bit more focus on regulation and treatment, quite a bit of interest in public customer interactions relations, and then some financial management of assessments. It's not just capital improvement plans, but emergency equipment planning as well. We will definitely work on these as we go into 2024. And please, like I said earlier, please sign up for notifications as we will be starting off January 2024 with a leadership development in-person workshop, and then we'll continue on from there into June. The audience sharing here will hide the poll. And like I said, I guess that can right here, go ahead, we'll conclude our, why won't it show my screen? Show my screen. There we go. That will conclude our webinar for the day. If there were any follow-up questions, comments that you want to present for any of our SMEs or subject matter experts that you listened to today, please feel free to contact them. Here is their email. If you stay till the entire event, please make sure you go to the handout section and take any the agenda and any copies of presentations that you would like to have. If you cannot access the agenda or any presentations, please email myself. My email is down at the bottom, roan.ebony@azdeq.gov. Or you can also email the OPCERT program azopcert@azdeq.gov, and we can email you a copy of the agenda. This webinar was recorded and it will be available on our YouTube page within the next couple of weeks. If you want to know where our YouTube page is located, all you have to do is go to our OpsCert homepage and look under presentation library on the sidebar, and it'll also have a link. Not only will there be presentations there, but it'll have a link at the top to the YouTube page. I want to thank you all for attending today and listening. We hope you took away something useful from this all these presentations, and have a great rest of your day and a very safe weekend.